Okay, so it's time to start. Okay, let's start the session for Quark and Lepton Flavour physics. And first speaker is David. David, are you connected?
Yes, hello.
Hello. Can you start? Can you share your screen?
Yes, I will. Okay, hi everyone. My name is David, and I will talk about the Electroweak penguin decays at LHCb.
It seems. Oh, okay, now I see. Okay, please.
Excuse me?
Please go ahead.
Okay, thanks. Electroweak penguin decays are flavor-changing neutral currents, which are forbidden at tree level and in the standard model, and can therefore only happen via quark loops, as shown in the following Feynman diagrams. Therefore, the decays are heavily suppressed, and that's why we call them rare decays, with branching fractions usually in the order of 10 to the minus 6 to 10 to the minus 8. However, in these quark loops, we can have new contributions from new physics models, like leptoquarks, Z primes, and many more, which would then warp the branching fractions and other observables. And we've observed tensions to the standard model predictions in these Electroweak penguin decays over the last year, which we usually refer to as flavor anomalies, and I will have a slide on this as well. At LHCb, we have a perfect working environment for Electroweak penguin decays. We're dealing with purely charged particles, final states, which are very beneficial for the LHCb detector, as we have no neutrinos and can fully reconstruct the final state. We benefit from a huge cross-section of BB bar production at the PP collisions, and the detector in general is optimized for observations of these decays with a very high trigger efficiency and very precise momentum resolution, and also the single particle identification is working well. So we have a huge data set of produced BB bar pairs and therefore B mesons, which we can then analyze. And in Electroweak penguins, usually we have different experimental probes that we can address. So differential or in general branching fraction measurements, test of CP conservation. A large topic is always angular observables, which I will also address. And last but not least, Lepton Flavour universality tests, which I will not address in this talk, but there's a dedicated talk on this from LHCb tomorrow. To understand and to evaluate the different results from all these measurements, we usually transform the full theory of the quark loops into an effective description using Wilson coefficient and Fermion operators. And the benefit here is that this is model independent, so any new physics contribution can easily be added up to standard model predictions, and it is possible to compare different measurements in the same basis. On the right-hand side, you see a usual Q-square spectrum. Q-squared is the invariant mass of the lepton system. And you can see that different regions are sensitive to different Wilson coefficients C. The already mentioned flavor anomalies are usually also shown in 1D or 2D planes of these Wilson coefficients. Here you see two different interpretations from two different theory groups from last year and even from this year, combining different results in the sector and also from Lepton Flavour universality. You can see that, for example, on the left-hand side, the standard model is indicated here at 0, 0. So this is only the new physics contributions to the parameters C9 and C10. And you can see that the global fit to these results is clearly deviating from the standard model prediction. On the right-hand side, you also see that the best value lies away from the central 0, 0. And this is what we refer to as flavor anomalies. The first measurement of LHCb that I would like to address is branching fraction measurements, differential branching fraction measurements in bins of Q squared. And you can see that the measurements in general lie below the standard model prediction. And this tension somehow persists over the last years. You see the neutral decays on top of B0 to K star, 0 mu mu, and BS to phi mu mu. And then you have the charge decay of B plus to K star plus, and B plus to K star plus mu mu on in the bottom row, as well with the B0 to K0 mu mu. However, the branching fractions are a bit exploited. So what we usually measure at the moment is angular analysis. And I would like to introduce you to the angular observables that we can measure with electroweak penguin decays. So on the left-hand side, you can see the topology of the decay angles, which are defined in the lepton system in blue, and in the hadron system, so usually K pi in red. And the angle phi is defined as the angle between the decay planes, which are spanned by the which are constructed by the two systems. Together with the Q squared, already mentioned Q squared, the decay kinematics can be fully parameterized using these three angles, and a differential decay rate is expressed. And this is a very lengthy term. You don't have to remember all the terms here, but the angular observables are indicated in blue with the longitudinal polarization fraction, the backward-forward asymmetry, and the S observables. And this is what we would like to measure and what we have measured. And with the first part, I talk about the update on the measurement in B0 to K star 0 mu mu. We have a 4-charged particle final state as the K star 0 decays to K plus pi minus. This has been measured before by LHCb with run 1 data and 2011 data. And the most exciting existing attention to the standard model is most prominent in P5 prime, which I will also have a slide on. You can see that updating this from run 1 on the top right to including 2016 data here is approximately doubling the statistics. So we get more sensitivity on the observables. The analysis strategy, we have a 5-dimensional fit to the masses of the B and the K star, as well as the 3 angles. And you can see example fit projections here on the right-hand side for 1 Q square bin. We also use the K star system to constrain the S-wave fraction, and is in 8 Q square bins. The acceptance correction is convoluted into the fit PDF, and we fit the run 1 and 2016 data simultaneously. These are the resulting values for the angular observables. You can see all 8 observables in trend in Q squared, and with standard model predictions in purple. The last plots basically don't have standard model predictions, but the observers are very close to 0. If you use the less form factor dependent observables, which are the P prime or P observables, usually a ratio of 2 observables, so S5 divided by FL times square root 1 minus FL in this case. The form factors cancel out to first order, and the plot on the left is basically the updated version of the famous tension, where you can see that the values here, the combined ones from LHCb in black, lie above the standard model predictions in orange. And well, this is only one presentation of where you can see that there's a tension here for the local bins between the J-psi resonance between 2.5 and 2.9 sigma. But the whole story is only told if you evaluate with a global fit all observables and interpret these in terms of Wilson coefficients. So that's what we're gonna do next. You see the new physics contributions here of the parameters Wilson coefficients C9 and C10 again, and you can even see them being split up here into the contributions from the different observables, so FL, AFB, S4, and S5, and you can see that these individual observables give a very consistent picture. And this is also something that was now achieved in the update. Also, on the next slide, you can see that the results between run 1 and 2016 are very consistent, and that they're very compatible with a C9 new physics scenario of -1. The overall discrepancy to the standard model value is 3.3 sigma. And again, on the right-hand side, you have the 2D plot where you also see that yeah, the previous measurement and the new measurement are in very good agreement. We come to the last point that we'll only scratch, because we have a dedicated talk on this as well in an hour or so about. So we have the same decay as before, but we exchange the electrons by muons. So we have B0 to K star EE at a very low Q squared by, so there's only one Q square bin, and by folding the angle phi in the following way, as mentioned in the bottom left, we reduce our angular decay rate and simplify the terms. You can see the mass projection on the right-hand side. So we have about 530 events in the signal region. And with this, we do, yeah, the fit to the 4 observables in this term. You see the fit projections here in the next slide. So the 3 angles and the resulting values for the longitudinal polarization fraction and the 3 defined amplitudes here are in good agreement with standard model predictions. And as I already mentioned, a detailed talk as well as interpretation in terms of Wilson coefficients will be at 9 AM by Martino. So with this, I would like to conclude. So at LHCb, we've performed the differential branching fraction measurements, which are consistently low. We have seen the update on the B0 K star mu analysis, including 2016 data. We see that the muonic electroweak penguins narrow down on a scenario of C9 compatible with -1. And yeah, LHCb in general is ramping up analysis with electrons, and we have exacting times ahead of us with also Belle II starting up. And then I would like to advertise further LHCb talks on electroweak penguins. As already mentioned, Lepton Flavour universality and rare radiative decays, plus the purely leptonic rare decays, which already happened on Tuesday. So with this, thank you for your attention.
Thank you very much. Any comments or questions? It seems not. Okay, so I have one quick question. So you choose the for B2 K star E analysis, you choose a very low Q square region, less than 0.25 or something.
Yes.
But the last time you take the, I think 1 GB squared.
Yeah, we reached a lower Q squared with the updated analysis. Yes. And yeah, I don't want to take too much information away from the presentation following at 9, but we reduced the background contribution in this Q square bin, and also the sensitivity on on C7 without interference from other Wilson coefficients is achieved by this very low Q-square bin.
Okay, thank you. So any other comments, questions? Seems not. Okay, thank you very much, David.
Thank you.
Okay, so next speaker is Alessio.
Hi, can you hear me?
Yes. Please
Okay.
share your screen.
Okay, can you see the sharing?
Yes.
Okay, I will try to go full screen. Tell me if, oh no.
I can see your slides.
Okay, so let's go with this. Okay, so I will present you now the CMS measurement for the B2 SLL decays. So I don't need to convince you that it's very important to measure, to study this flavor change in neutral current decays, and the fact that they are doubly suppressed in the standard model makes them very good laboratory to probe, to look for new physics effects through angular analysis and branching fraction measurement. In CMS, we focused so far on two kinds of decays. The pseudoscalar state decay, B plus to K plus mu mu decay, where thanks to the using the muon direction, we define one angular variable in this decay that allow us to measure the muon forward-backward asymmetry and an additional angular parameter FH. And the vector state decays B to K star mu mu, where we have a muon direction and the K star polarization that define three angular variables that allow to measure a large set of angular parameters that are sensitive to the Wilson coefficient that David presented a few minutes ago. So these channels are also very accessible from the experimental point of view, thanks to the fully charged final states and to the easy to identify pair of muons. Okay, so with the RAN1 datasets, CMS already published several measurements. We have the measurement of the B plus to K plus mu mu. You can see here the AFB and FH results. We have several measurements on the B0 to K star 0 mu mu. Here I show you the FLAFB P1 and P5 prime results. But in this talk, I won't talk about this analysis, but I will talk about a new decay that was just published about the B plus to K star plus mu mu analysis. So this decay can be fully described by three angular variables and the muon invariant mass. This analysis is performed integrating out the phi variable, so leaving the angular decay rate as I show you in this formula here. And as you can see, this depends on FL, which is the fraction of longitudinally polarized K stars, and AFB, which is the muon forward-backward asymmetry. So we want to measure these two parameters, and we do this in bins dividing the Q-square range in 5 bins, 3 of which containing the signal where we perform our measurement, and 2 of which containing the resonant decays with the JPSI or Psi2S that are used as control channels. In addition, this analysis is performed on the merging the 3 signal Q-square bins. Okay, so the events are selected by using a trigger requiring 2 low PT muons, forming a displaced vertex and with low invariant mass. The K star is reconstructing through its decay in a K short and a pion, and a K short in its decay in 2 pions that are, and we reconstructed by looking for a 2-track vertex in our detector that is displaced from our B decay vertex. We apply, in order to reduce the background contamination, we apply mass and vertex quality requirements on the K short and the K star candidates. And we apply a veto in order to exclude the lambda 2 proton pion decays. In addition, we have several selection on the momenta of our components and on the vertex quality and displacement of the B. And these are optimized in order to maximize the signal significance. We add a combined cut also on the Q square and mass of the candidate B+, in order to exclude the contamination, the leaking contamination from the resonance channels. You can see on the bottom the spectra for the mass spectra after the selections for the 3 Q square beams, together with the signal yield we measure in each of them. Okay, so in order to parameterize the efficiency, we want to do that using a 2-dimensional function and starting from a sample of simulated Monte Carlo. We do this in 2 steps. First, for each of the 2 angular variables, we fit 1-dimensional function defined as polynomial or combination of Gaussians. You can see the 2 of them here in the formula. Then we fix them and we fit the 2-dimensional efficiency and we fit it for a correlation term that is a product of Legendre and ordinary polynomials. You can see on the right an example for the IQ square beam of the 1-dimensional projection of the efficiency and its description. Okay, so this is the PDF we want to use for the fit. In the first line, you can see the signal component that is composed by double Gaussian mass shape here, whose parameters are determined on Monte Carlo simulation and fixed to the fit to the data. And then the decay rate and efficiency function that I already shown you in the previous slides. The second line is the background component with an exponential mass shape and 2 angular shapes, angular components that are 1-dimensional function combination of a polynomial or Gaussian or exponential shapes. Okay, with this PDF, we perform the fit in 2 steps. First, we fit the mass sidebands in order to determine the background angular shape that is then kept fixed. And then we fit the whole mass spectrum with 5 floating parameters, the 2 yields, the 2 angular parameters we want to measure, and the slope of the background. All these are unbinned extended maximum likelihood fit. And in order to have a robust estimation of the statistical uncertainty, we apply a profiled Feldman-Casin method. Okay, here on the top you can see the result of the fit, the 1D projection of the fit result for the IQ square beam. Here consider that the 2 angular projections are shown only in correspondence of the signal peak. Okay, the projection for the whole mass spectrum and for the other Q square beam can be found in the backup. Here on the bottom you can see the 4 sources of systematic uncertainties that we consider. The dominant one you can see that is the one coming from the background description, and is taking into account 3 effects: the choice of the function we use to describe the background, the extension we set for our sideband, and the propagation of the statistical uncertainty of the sideband in the second part of the fit. Okay, and here you can see the results. In the black points, the inner error bar is the statistical uncertainty, and you can see that it's the dominant one. And we compare them with the standard model prediction, and showing this comparison, as you can see, shows full agreement between the results and the predictions. Okay, so the second study I want to talk about is the prospect for the B0 to K star 0 mu mu analysis at high luminosity, LHC. The goal of this study is to extrapolate the uncertainty on the P5 prime measurement in this decay with the high luminosity scenario at 3 in Borsato born. So we use the run 1 result of this analysis as a baseline. we considered the improved mass resolution that we expect from the upgraded tracker detector. You can see in the plot on the right, it's clearly visible the improvement in the mass resolution, and in the bottom one you can see this improvement across the Q-square range. And in addition to this, we don't add, let's say, for simplification, we don't add improvements in trigger performances or analysis strategy. The signal yield expected for this decay has been obtained from Monte Carlo simulation with the phase 2 detector upgrade and a pile-up of 200. And scaling to the luminosity of 3 in Borsato barn, we get about 700,000 events in the full Q-square range. So using this number, we can scale the run 1 statistical uncertainty and also the systematic uncertainties that are based on the data control channels. And for the other systematic uncertainties, we scale them by a factor of 2, assuming a general improvement in the analysis strategy. And in total, our expected uncertainty improved by 15 times with respect to the run 1 result. You can see on the right plot the comparison with the blue line that are the run 1 result. And in addition, this large signal yield that we expect will allow us also to split the Q-square range in finer beams. You can see here an example in the bottom part of the plot, an example of beam splitting in order to achieve statistical uncertainty that is of the same order of the systematic uncertainty. And you can see that here at low Q-square, this binning is pretty fine. Okay, so to summarize, well, with the run 1 data set we collected at CMS, we extensively studied these B2 SLL decays. In addition to the 2 decays that we are showing, let's say we show in past years, the B0 to K star mu mu and the B plus to K mu mu. Now I've added also the analysis of the B plus to K star plus mu mu to measure FL and AFB. And I show you also prospect for the B0 decay at high luminosity. But what about the run 2 analysis? Okay, we had a dedicated trigger requiring 2 muons and one additional tracker from a common vertex that collected a huge amount of data. And we expect more or less 15 times the signal yield we had in 2012 by combining the data set collected in 2016, 17, and 18, and a better signal to noise ratio. So in addition, more decays channel, we plan to explore more of them. So stay tuned for very interesting results.
Okay, thank you very much. Any comments or questions?
I have one. I didn't remember the number of slides, but where you compared your results with standard model in one bin, there were not standard model prediction. Yes, from 10 to 14. Why is it so?
Yeah, exactly. This is due to the fact that I suppose in this bin the presence of the contamination from the resonance channels is making the prediction less reliable. So no prediction has been provided for this Q-square bin. It's basically due, yeah, to the presence of the 2 resonance channels and their contribution. You can see that also in other bins, in other analysis, also the last Q-square bin below the GPSI resonance lacked of the prediction, and this is for the same reason. I don't know if in the CMS results I'm showing here. Yeah, for example, the B0 to K star mu mu, you can see that also the latest Q-square bin before the GPSI is missing this, and this is the same reason.
Yes, thank you.
Okay, so Para?
Yeah, thanks. Thanks, Alessio, for this talk. So I was wondering if you could comment on the prospects for B2SLL analysis at CMS with electrons, and in particular with your PARC dataset.
Yeah, this is something that, here you're asking about angular analysis of the electron.
Well, not only, just B2SLL in general with electrons,
okay.
Yeah.
Okay, so yeah, as you know, we collected a large sample of unbiased data. So we have also the electron channel available there in 2018, and we have let's say several active analyses that are targeting our, let's say, it's our priority to measure the R ratios for RK, RK star, and others. So these are activities that are ongoing. Let's say the reconstruction of low PT electrons are something new for us, for CMS. So it's something we spend a lot of time on, a lot of effort, but I hope results will come soon.
Okay, thank you.
Okay, so thank you very much. So let's move on to the next talk. So Anna.
Good morning, everyone. I'm here.
Good morning. Can you share screen?
Yes. Could you see the screen?
Yes. Please go ahead.
Okay, so I can start. Can I start?
Yes, please.
Yes. Okay. So good morning, everyone. I will speak about the rare decays of lambda B, BC, and other b-hadrons at the LHCb. In particular, I will speak about the rare decay of lambda B on behalf of the LHCb collaboration. Why we want to study the rare decay? Since this decay are mediated by flavor changing neutral currents, so they are forbidden at the level in the standard model and can proceed so through amplitude involving Electroweak loop. So they are sensitive to new particle at higher scales that direct research. The new physics, the new physics contribution could enter at the same level of the standard model, and so they could enhance or suppress the decay rate, modify the angular distribution or distributions, or introduce a new source of SIP violation. We have already seen several deviations in differential branching ratio, angular and CPO observables in B2SLL. You have already speak about this with David if you talk ago, and with Carla Marin of the Lepton Flavour universality measurement at the LHCb. All these measurement results dominated by statistical uncertainties, so we need to do an update of the previous measurement with the larger data set, but also look for complementary observables. So this talk will be focused on the baryonic B2SL transition that are sensitive to different spin structure beyond standard model defect, and we can use that since at the LHCb we produce a copious amount of lambda B. I will present three new measurement test of the Lepton universality with lambda B to pKLL decays, the first observation of the radiative decay lambda B to lambda gamma, and the angular moments of the decay lambda B to lambda mu at low hadronic recoil. The first one This test is a new test that is complementary to RK K star because of non-zero spin. The ratio is expected to be close to unity in the standard model. This measurement has been performed using 4.7 factor bar inverse of LHCb data. And the measurement is performed as a Debord ratio. The Debord ratio that we are seeing here, considering the channel lambda b to pk AA, normalized to the resonant channel lambda b to pk j psi, divided the correspondent ratio considering the muonic decay. The region of interest that we are using are chosen so that they are far from charmonuim and the muon threshold, and so that we avoid the multiple overlapping lambda resonances of different J. This is a challenge measurement, and in particular, the challenge is due to the different way on which the muon and the electron interact with the detector. So we have to consider the Brestaring effect and the different trigger cut that you have to apply for different interaction with the calorimeter of muon and electron. This measurement, the dominant background are the random tracker combination solved applying a multivariate approach, the hadron misidentification such as the BS2KLL, and the partially reconstructed background. We performed two separated fit to resonant and non-resonant channel, and the simultaneous fit to electron and muon mode for different data taking periods and trigger categories. The main systematical uncertainties are due to the partially reconstructed background shape in lambda b to pKAA. In this plot, you can see the yield that we found, the RK-RPK ratio that results compatible with the standard model and previous air measurement. The second analysis that I want to speak about with you is the force observation of the radiative decay lambda b to lambda gamma. This decay proceeds via flavor changing neutral current transition, so they are forbidden at 3 level in the standard model and sensitive to new particle entering in loop. Moreover, this decay offers a unique benchmark to measure the photon polarization due to non-zero spin for the initial and final particle final states. The branching ratio is expected to be in the range of 10 to -7 to 10 to -5. The large uncertainties are due to the lack of the form factor measurement. And the only previous limit that we have is a measurement of CDF. This channel is experimentally challenging to reconstruct since we can reconstruct the lambda b vertex due to the long lifetime of the lambda b baryon and due to the unknown photon direction, since it is reconstructing only as a cluster in the calorimeter. So it's not possible to reconstruct the lambda b vertex, and so use the displacement with respect to it. For the neutral pions, the contamination due to the neutral pions, we use a tool that suppresses it by exploiting neutral particle identification tool. The dominant background is formed by real baryons and random photon, and then another important background that we consider in the fit is the lambda b to lambda eta. The yields are to obtain normalizing our channel with respect to the B0 to K star gamma. This is the expression that we have to solve, where the ratio of the hadronization factor has been taken by a previous LHCb measurement. The branching ratio in blue are taken by PDG, and the ratio of the efficiency is derived by simulation and calibration sample. Simultaneous extended maximum LHCb has been performed, and here on the plot, in this plot, we can see our signal, and here in the dashed line, we can see the normalization channel yields. This is the first observation of lambda b to lambda gamma, and this is the branching ratio that we have obtained, where the first one is the statistical uncertainty, the second the systematical one, and the third one the systematical due to external input. The last measure that I want to speak about is the angular moment of the decay of lambda b to lambda mu at low hadronic recoil. So in the extension of the standard model, the angular distribution can be modified significantly. We have already seen anomalies in B2 K star mu. And what are the differences using the baryonic channel? The difference is that lambda B is a spin alpha, can be produced polarized. The transition involves a d-quark system as a spectator, and the lambda decay, lambda decays weakly, and the lambda that we are considering decays weakly. So important additional test of the standard model prediction can be done using this channel. This is the first measurement based on the full basis of angular observables of this decay. The analysis is focused on the range of between 15 and 20 GeV of invariant mass of the Lepton system, Q square, and the dataset used include 5 femtobarn inverse of data collected by LHCb detector. This analysis exploits the method of the momentum, and the full angular distribution can be described by a sum of 35 terms. This is the expression where omega include all the angles that you can see in this figure. Theta, theta 1, 2, and phi1 and phi2. K are the coefficient which depend on the underlying short distance physics and on the form factor, and Fi are the angular functions. The angular distribution can be described by these 5 angles and the invariant mass of the Lepton system. The K parameters are determined using the method of moments. The background is subtracted, obtain a fit of the invariant mass of our decay. Then the angular distribution has been distorted by trigger reconstruction and selection. So we need to correct the angular efficiency using the lambda b to lambda mu simulated events. And then we perform a cross check using the b to j psi k short and lambda b to lambda j psi decays on the data. All parameters that we have found, you can see in this plot, result compatible with the standard model prediction. The larger discrepancy can be seen in the K6, that is 2.6 sigma from the standard model prediction. The K11 to 34 result to be equal to 0, and so this result is compatible to have no initial lambda b polarization. We also measure the asymmetry, the angular asymmetry. And we found that the only one that is connected to the K6 results 2.5 sigma from the standard model prediction. The other one are in agreement with that one. So in conclusion, the rare decay are useful tool to search for new physics beyond the standard model. We have several hints with respect to the standard model prediction in the B2SL transition in differential branching, angular observables, and in test of Lepton Flavour universality. Rare baryonic decays are sensitive to a different spin structure, so they are the study of these decays are a complementary measurement necessary to try to understand what is happening, and at the moment all measurement result dominated by statistical uncertainty, so we need to perform the update of the existing analysis to confirm the result and to look for new complementary measurement. Thank you.
Okay, thank you very much. Since we don't have enough time for questions, please go. If you have a question, please go to Matamos chat. Okay, so let's move on to the next talk by Yo.
Good morning. Can you hear me?
Yes. So please share your screen.
So now is it full screen?
Yes, we can see your slides.
Okay, so I would like to start. So I am Sato. It's a pleasure to present on behalf of Belle II collaboration the result and prospect of radiative and electroweak penguin decays at Belle II. Okay, I would like to start from the introduction. So the flavor changing neutral current B2S and B2D processes continue to be a great role for new physics beyond the standard model. Especially radiative and electroweak penguin decays are theoretically and experimentally clean because the final states include color singlet particle or particles like a gamma to lepton or to neutrinos. And recently, the anomalies are observed in the B2K or K-style L decays, and they highly motivate further study on this field. And Belle II can contribute the radiative and electroweak penguin decays with many observables. Here I picked only 3 items. The first one is the time-dependent CP vibration in radiative decays. So in the standard model, B2S gamma with right-handed gamma is helicity suppressed, but the new physics can induce much larger decay rate of B2S gamma with right-handed gamma, and which introduce large mixing-induced CP vibration. At Belle II, B2K star gamma was rediscovered at last summer. An update with a new data set of this analysis is in progress. And second is the measurement on inclusive B2XSLL decays to shed further light on the anomalies of exclusive B2SLL. And third is the discovery of channels involving neutrino, like B2K or K-star nu. And this table is taken from the Belle II physics book, so there are more observable to search the new physics. But today, I would like to focus on these 2 items in this talk. Then I would like to start from the B2XSLL. And before that, I would like to remind of the theoretical basis and the status of B2SLL. B2SLL is related to C7, C9, and C10, which are the Wilson coefficient of effective Hamiltonian. So that these are the relevant operators to this process. And C7, C9, C10 are the following value in the standard model. And C9 and C10 are same for electron and muon because of the Lepton Flavour universality. But the recent anomalies in exclusive B2SLL implies smaller C9, especially for the C9 of muon. And this is an example, so which is the P5 prime by Belle experiment. So in this figure, so in the second bin of Q square, a muon mode has about 2.5 sigma discrepancy from the standard model. And Belle also performed the study on the electron mode with almost same precision with muon mode. It is an advantage of the electron-positron collision experiment to test the Lepton Flavour universality. And this situation motivate the inclusive B2XSLL study. In the B2XSLL, the hadronic uncertainties are under better control than the exclusive B2SLL. And so far, Belle and Bava performed the analysis on B2XSLL with some of exclusive method. So XS is reconstructed from many final state. But many final state are reconstructed, and so there are large backgrounds. So this study is experimentally challenging. And so far, all observables are highly statistics limited. And this is the result on the forward-backward asymmetry by Belle. And this red band is the standard model expectation. And so far, the measurement is consistent with standard model, but the error bar is still large. And Belle II is the unique experiment to perform an analysis on B2XSLL with large statistics. Then I would like to show the result and the prospect on the B2XSLL in Belle II. So as baseline, also the sum of exclusive method is adopted in Belle II. XS is reconstructed from K and pi with n is up to 4 and the 3K final state, allowing at most 1 K short and 1 pi 0. And MXS is required to less than 2.0 GeV to suppress the background. And higher MXS region will be explored with large statistics. And the dominant background of this analysis is so-called double semileptonic decay, which means that both B meson decay semileptonically. And also misidentified B2K and some pion final state has to be understood to control the peaking background. And this figure shows the beam constraint mass distribution of the B2XSLL with Monte Carlo simulation. So as shown here, so signal peak is very clear compared with the background. And this table shows the sensitivity on branching fraction and forward-backward asymmetry. So with 15 Borsato band, the sensitivity on branching fraction and forward-backward asymmetry is a few %. And also the fully inclusive method will be explored with dedicated simulation study in future. Okay, then at the end of this topic, I would like to show the interplay of inclusive and exclusive B2SLL. So in this figure, contours shows the sensitivity from the inclusive B2XSLL on the C9 and C10 from new physics. So 0,0 consistent standard model. And this blue line corresponds to 5 sigma constraint. And this red region is the result from the exclusive analysis. So as shown here, analysis of inclusive B2XSLL with 15 Borsato band will exclude the standard model by 5 sigma if the true values of C9 and C10 are the current best fit. And note that the hadronic uncertainties in the inclusive and the exclusive decays are independent. So complementary information can be provided. And not only the forward-backward asymmetry, full angular analysis can be performed with large statistics, which provide the independent constraint on the parameter space. Okay, then I'd like to move on the next topic, B2S nu. So this process is theoretically cleaner than B2S LL due to the absence of photon-mediated contribution. So in the standard model, only this OL operator is relevant. But there are 2 missing neutrinos, so this study is experimentally very challenging. And so far, the decay has never been observed. So this is the result from the Belle, and this is the standard model expectation. So the current upper limit is close to the standard model, but they are not reached to the observed. And Belle II can observe the B2K and K star nu at early stage with several inverse advance. And to identify the signal, the missing energy or momentum will be used by reconstructing the other side B meson. And conventionally, the hadronic and semileptonic tagging will be used. And once this decay is observed, the more precise study will be performed. And the sensitivity on the branching fraction is 10% level with 15% advance. And for the B2K star nu, the longitudinal polarization fraction can be measured with 20% precision. And combining B2K nu and the B2K star nu result will exclude a large portion of allowed parameter space. So this figure shows the CL and the CR from the new physics contribution, and which are the Wilson coefficient of this operator. And this white region is the current allowed space, and these color bands are the sensitivity from the Belle II. So as shown here, the Belle II will set the strong constraint on the parameter space. And an analysis with new tagging method with current data set is in progress for the publication. Okay, then I would like to conclude my talk. Belle II collected about 74 inverse per integrated luminosity by this summer. And 10 times more data is taken in this summer than the last summer. So data taking going very smoothly. And the measurement in various processes has been started. And the first result in B2SLL and the B2S nu in progress. Belle II will collect 50 inverse advance by 2030. Then we will confirm or exclude the anomalies with B2XSLL, and we will discover B2K and K star nu at early stage, and the precise measurement will be performed. So please stay tuned for the future update of Belle II study. Okay, this is all. Thank you very much.
Thank you very much. Any comments or questions to you? It seems not. Okay, so how much luminosity is needed to discover B2K nu or K star nu?
Okay, so yes, I said several inverse advance, but especially for B2K star nu, we may need about 5 inverse advance.
Okay, thank you. So any other comments, questions? It seems not. Okay, so thank you very much, Yo.
Thank you.
Okay, so next speaker is Martino.
Yes, can you hear me?
Yes, I can hear you.
Okay. So,
Please go ahead.
okay. Thank you very much. Yeah, so good morning, everyone. Thank you for connecting today. I'll be talking about rare radiative decays at LHCb, which basically means the transition B to S gamma. And this is a golden channel of B physics, as it is a flavor-changing neutral current, which is mediated by an electroweak loop with the W on the top. And their virtual BSM contributions can be large. And on top of that, is not so rare. So we've been hearing about 10 to the minus 6 and 7 for rare decays, but the inclusive branching ratio for B to S gamma is about 3 10 to the minus 4. It is described, can be described with an effective Hamiltonian, and for B to S gamma, the relevant operator is the electromagnetic dipole operator as O7, which is multiplied by the Wilson coefficient C7. And an important characteristic of B to S gamma is that the photon emitted is mostly left-handed in the standard model. There are just small right-handed contributions coming from the Mars insertions on the external quark legs. So they go as MS over MB, which is very small, 0.02. And therefore, a measurement of the polarization of the photon from B to S gamma can reveal tiny, beyond standard model, right-handed currents in the loop, as due, for example, to heavy vector-like quark masses. How about LHCb? Well, LHCb is very well suited for rare decays in general, and we have about 10 to the 12 BB bar in the acceptance if you sum from the whole data set. And we collect all kinds of Bs, BD, BU, BS, and lambda B. LHCb, I should mention, is best at the reconstruction of charged particles such as muons, pions, kaons, and protons, but there's a price to pay if you want to reconstruct neutrals, such as a photon, which of course is very relevant for radiative B decays, but also pi 0, k short. And also, if you want to reconstruct an electron, as at LHC energies, they are very boosted and they emit Bremsstrahlung before the magnet, and our Bremsstrahlung reconstruction efficiency is only 50% efficient because of the very busy environment at the LHC. And the hardware trigger is key, if you want to trigger on the electromagnetic signatures such as electrons and photons, you have to take into account that the trigger threshold is about 1 GeV larger than the one on muons, and therefore you pay a large price for that. And but we will upgrade the trigger and move it completely to software starting in 2021. I also wanted to mention that depending on your final state, if you have muons, electrons, or photons, as you see in the plot on the top right, your momentum resolution for these particles is different, and therefore the reconstructed B mass will have a different resolution. So you see it is best for muons in blue, and then for electrons it is a little worse, and you get a large tail on the left due to Bremsstrahlung loss, and in the case of the photons, you get a large Gaussian due to the electromagnetic energy resolution. So how do we go and measure these C7 and C7 prime Wilson coefficients related to B to S gamma? Well, the left-handed C7 is measured mainly with branching ratios, and in particular, since the inclusive branching ratio is predicted with much more accuracy, we reached about the 5% level. Then this is measured best at B factories, and they already reached the level of the theoretical precision. And at LHCb, there's really not much we can do about that. Inclusive branching ratios is really hard. And concerning instead the imagery part of C7, you can measure that with the direct CP asymmetry, and this was done at B factory with short pi 0 gamma, and at LHCb we can use B sub s to phi gamma. Then if you move to the right-handed side, C7 prime, which is very small in the standard model, as I mentioned, we can measure that with measurement of observables that vanish in the standard model. So, for example, there's the mixing-induced CP asymmetry in B2K short pi 0 gamma, which was measured with factories. But at LHCb, we can use b sub s to phi gamma, a full amplitude analysis of b to k pi pi gamma, an angular analysis of lambda b to lambda gamma, and also transverse asymmetries in b to k star EE at very low Q square, where it really resembles b to k star gamma. And today, I will be talking about a new result in b sub s to phi gamma with run 1 data, and very, very new, presented just in this talk now for the first time, results on b to k star EE, measured with the full data set. So starting with b sub s to phi gamma, well, this is, LHCb is uniquely placed to study these decays, of course, because we get plenty of b sub s. We have a signal yield of about 5,000 events with only the run 1 data set. And there is a large background, but it's mostly combinatorial, and we can keep that under control. And we can also use the b to k star gamma channel as calibration. And the thing is, as you know probably, is that the large width difference between the the b sub s and the b sub s bar allow to extract the mixing-induced asymmetry from an untagged sample. And this we had done already in, I believe, 2015. And now we also plugged in flavor tagging, which is not as good as in b-factories at LHCb, where we reach a level of 5%, which is pretty good given the yields we have. And this is actually large enough for a time-dependent analysis, flavor tagged analysis. And we extracted observables that are flavor tag independent, such as CCP and SCP in the formula below. And so this is the results of the free inverse Fentobel analysis. We remeasured A delta. This supersedes the previous results, and we measured the CP observables S and C. And you see that these are the most precise measurements to date. I think the only one for actually. And the systematics are mainly coming from decay time resolution and tagging efficiency, and these are very compatible with standard model prediction. And also they are still statistically limited, so we expect better results with run 2 analysis. Okay, so moving on to the very new result today. It's about B2K star EE, which is a B2SLL transition, not strictly speaking a B2S gamma, but if you go to the very low Q square end, where the B2S gamma pole dominates, it is really just the same as B2K star gamma. And we are able at LHCb to select a large sample of this decay at very, very low Q square. We go down to 0.25 GeV square. And there, the pollution from other diagrams, such as the vector and axial vector currents, are negligible. So we are really looking at B2K star gamma here. And the standard model branching ratio is just 10 order 10 to the minus 7 here, but we get a fully charged final state now, no photons. So the K star plus, the K star goes to K plus pi minus, and we have two electrons. And at this low Q square end, the semileptonic and combinatorial backgrounds are phase space suppressed. And you can see that in the plot in our fit to the signal in the B mass region, and you see that the signal is very pure for an decay with electrons with the branching ratio 10 to the minus 7. So we did the analysis with the full data set collected so far, and this allowed to go even lower in Q square, and we get about 530 signal event with extremely low background. So we have to do an angular analysis of that. This was already introduced by David. Here we simplified the expression in David's slide by folding the phi angle. We end up with just 4 angular observables. There's one you recognize is the longitudinal fraction, FL. Then there's AT real, which is related to the forward-backward asymmetry. And the two we're most interested in are AT2 and ATIM. As you can see in the equation on the bottom left, they are related to the B2K star gamma photon polarization. Yeah, so there's, as you can imagine, B2K star gamma has a much larger branch ratio. And if the photon converts into detector material, it has the same final state as B2K star E. So it is a background to us, but we can well separate it using a material veto and most importantly, a cut on the dielectron mass. We require it to be larger than 10 MeV, and we get rid of all the photon conversions, basically. But actually, this sample is a good control sample for B2K star EE, and we use it because it has very similar signal shape and background composition, and we can fit, for example, the K-pi EE mass distribution to validate the signal fit. We get about 3,000 B2K star gamma candidates there, as you see in the plot on the top. And then we can also fit the angles, actually, the cos theta K angle, which is related to the K-star polarization. And since here the photon is real, we expect the longitudinal polarization to be 0. And we measure that to be compatible with 0 with sub% precision, thus validating our fit to B2K star EE. So moving to the fit to B2K star EE, this is a 3-dimensional fit in the angles plus one more dimension to fit the B2K, sorry, the K-pi EE mass as to separate the signal from background. And yeah, I already mentioned that the background is really small. Of course, we need to model those in the angular dimensions as well. And for that, we use samples of Monte Carlo, but also B2K star mu E candidates that are mostly composed of combinatorial background and semileptonic, double semileptonic. So these are the results we get for the 4 angular observables. This is a big improvement with respect to run 1. Let me comment that the statistical errors dominate. And the measurements of the longitudinal fraction and of the ATRE, which is related to the forward-backward symmetry, are also interesting in the context of B2K star mu angular anomalies. You see, for example, in the plot on the bottom, a comparison of these measurements to the one in the muons, which are the black points. And yeah, these measurements is sensitive to a region which is very complementary to the muons in the extremely low Q-square end. So, and on top of that, this analysis prepares the ground for lepton universality tests in angular analysis of B2K star LL. So moving to the most interesting observables, AT2 and ATIM, those are sensitive to the B2S gamma photon polarization. And if we look at these, the constraints they imply in the complex plane of the right-handed C7 Wilson coefficient, which is related to B2S gamma photon polarization, you see that compared to previous results from both B factories and LHCb, this is extremely sensitive. So it's the red circle compared to the others. And we can constrain with this analysis both the real and imagery part of C7 prime, and the constraint is better than the combination of all previous results. This is still statistically limited, so the upgrade will bring interesting information. Okay, so conclusions. Well, I think we can say that the LHCb program of B2S gamma studies is flourishing right now. We just achieved a world best measurement of the photon polarization in B2S gamma. And we have methods very different from B factories. So I guess this was kind of unpredictable. We have time-dependent and analysis of B sub S to phi gamma, and the angular analysis of B2K star E at very low Q-square. And you should expect more precise results from run 2, such as the update of B sub S to phi gamma, and also from the upcoming LHCb upgrade. Thank you.
Thank you very much. Any comments or questions? It seems not. Okay, so I have one question. For B2 Kesta EE case, I think brainstorming recovery is very important.
Yeah.
But for low-Q scale region, I think one photon can be attached to both electron or positron. So you might misattach the photon. So how do you treat these events?
Yeah, this is not a large fraction of events. It really happens. So it really happens often for dielectron conversions. You're right, but as soon as you go to larger dielectron mass, this doesn't happen so often. Anyhow, we found that the best way to the most unbiased way to treat this is to add randomly the Bremsstrahlung photon to either of the electrons.
Mm-hmm. Okay, thank you very much. Okay, so any other comments, questions? It seems so. Okay, so thank you very much, Martino.
Thank you.
Okay, so let's move on to the next talk by Semen.
Yes, hello, can you hear me?
Yes, I can hear you.
Okay, let me share the slides. I hope you can see them now.
Yeah, please go ahead.
Okay, so I'm going to tell you about atlas studies of exotic sense spectroscopy, and particularly my talk will be devoted to the recent result that we released on the study of the pentaquark resonances in the JSI proton system of the lambda BDK using the RUN1 dataset. I will summarize the current experimental situations regarding the pentaquarks with hidden charm and outline the atlas analysis strategy, focusing on the fitting strategy and in particular on how we study the physics background from neutral B-meson decays and the actual lambda B decays, show comparisons with the results from LHCb on these pentaquarks and with the null hypothesis, and outline the conclusions and plans. So the story of the pentaquarks with hidden charm dates back to 2015, when LHCb reported an observation of two structures in a JSI proton mass system of the lambda B decay into JSI proton kaon. They also evaluated their spin parity and later reported an evidence for the same states in the lambda B to JSI proton pion decay. And a little bit later, also a model-independent study showing evidence for existing of these states came. Later, LHCb reported another study of these states using the full RUN2 dataset, where they resolved the initial narrow states at the mass of 4450 into two even more narrow states, and also discovered a new state at the mass 4312, which was not reported before. These narrow states show well-defined resonant behavior, and their masses are near sigma c d star threshold, while status of the wide resonance of the mass 4380 reported in their first observation is less clear. It's also interesting to note that these states were not observed in photo production by GLUE-X experiment that may be explained by low branching fractions of these pentaquarks into JSI proton. Okay, moving on to the atlas analysis. So the main challenge that we faced in our experiment is that atlas lacks particle identification. Therefore, we have to consider all possible decays of b-hadrons to JSI and to charge hadron track candidates. And to properly study all these type of events, we have to model all these decays of lambda b, b0, b sub s, considering all possible intermediate states such as lambda star, k star, f in the system of light hadrons, and also actually the pentaquarks as intermediate resonance in the system of JSI proton. We model these contributions mostly with analytical matrix elements, which include coupling constants to all these intermediate resonances, which are actually extracted in our feeds. combinatorial background shapes are described using the events from the lower mass sideband of the lambda b mass distribution, which is dominated by the background of combinatorial background events. And for our fits, we define certain regions corresponding to the signal area, which is enriched by the lambda b events, and the control regions enriched with B0 and B sub S decay events. Of course, in all these regions, B0 decays are actually dominant, while lambda b contribution to the control regions of B0 and B sub S is very small. Okay, so this slide summarizes our fitting strategy. Due to complexity of the fit, it is done iteratively. So at each iteration, we perform 4 steps, allowing us to extract certain parameters which are free in the fit. And after each iteration, we use the values extracted at that one to fix some parameters at particular steps of the next iteration. And we stop the iterative procedure if there are no sizable changes. In our case, the data fit converged after 4 iterations. At each iteration, we have 4 steps. The first one is a global fit, which we use to extract the coupling constants for B0 and B sub S decays, our main physical background. And it uses a variety of distributions in the global scope and in the B0 and B sub S contour regions. The second step, we use the invariant one distribution of J-psi proton kaon system to extract the yields of lambda b, B0, B sub S decays and the combinatorial background. And at the third and fourth steps, we actually study the signal region and use it to obtain the decay constants of lambda b, including those related to the pentaquark intermediate resonances and the actual parameters of the pentaquark states, their masses, widths, and the yields, which we extract using the invariant mass distribution of the J-psi proton in the signal region. Okay, so let me try to summarize basically these steps. So in the global fit, we extract the parameters of the B meson decays, which, as I said, are the main physical background for our processes. And to do it, we use simultaneous fit of the invariant mass distribution of the J-psi with 2 charged hadron tracks under different kaon and pion mass hypotheses, which are shown here. And as you can see, they are sensitive to separating the different decay contributions. And at this step also, we use distributions of the mass of J-psi with one of the 2 hadrons and mass of the 2 hadron tracks in the B0 and B sub S control regions, which you can see at this slide. These distributions actually adds the major part of the sensitivity to the coupling constants of the B0 and B sub S decays. Okay, so once we fix the B0 decay parameter set, the first step, we go to the study of the lambda b decay and the signal to extract the yields of lambda b and B0 B sub S decays. We use the distribution of mass of J-psi proton kaon that is shown here. And as you can see, after our event selection, we have about 2,300 lambda b decay events in the global scope. That means in the full selected samples. And further study of our signal is done in the signal range, which is shown here by the dashed lines. And in this signal range, we retain basically half of the lambda b decay events. Okay, so at the third and fourth steps of our fit, we actually extract the parameters of the pentaquark resonances in the J-psi proton system. And here in the table, you see their parameters. So we have totally 540 events with decays occurring through the 2 pentaquark states. And in our nominal fit model, we consider the 2 pentaquark states, which were originally reported by LHCb. the narrow one with mass around 4450, and the wider one with a mass around 4380. So we extract the masses and widths of these states, which are shown in the table here. You see that generally agreement with the original LHCb result is fairly good, except maybe the mass of the white pentaquark state, which is somewhat smaller, but still consistent within 2 standard deviations. If we fix the masses and widths to the original result of the LHCb, the agreement with data is still good. You can see the chi-square over NDF value here. Of course, we try to check how consistent our data are with the most recent result of LHCb, which included the new narrow pentaquark state. Unfortunately, at this point, we cannot distinguish them in Atlas due to worse mass resolution. But what we did, we checked the chi-square, fixing all the parameters of these new states to the LHCb result. And as you can see, the compatibility is still as good as in our nominal fit. Okay, so this slide shows some control plots for our fits with the hypothesis, including the 2 pentaquarks. These are distributions for J psi kaon and proton k invariant masses, which are also sensitive to these intermediate resonance contributions. They show pretty good agreement with data, as well as the angular variables shown on bottom, which were not used in the fits, but still somewhat sensitive to all these intermediate resonance contributions. Okay, so at this slide, there are tables summarizing the systematics. I won't tell much about this, just mention a couple of interesting sources. The first one is the modeling of non-pentaquark lambda B decays that we tried to extend to an alternative, more complicated lambda star decay model, allowing for 2 lowest orbital momenta of lambda star decay products for certain lambda star resonances, which is more complicated, but allows to describe the data a little bit better than for the nominal case in the absence of pentaquarks. And for the B-meson decay modeling, we additionally allowed for contribution of ZC4200 state as an intermediate resonances in J-psi pion system. In the nominal model, we didn't have it, as our data are not quite sensitive to it at this stage, but we used it as an alternative variation for systematics. Okay, and actually the question is how consistent would our data be without the pentaquarks in the model? So we repeated the fit procedure with the lambda B decay model without pentaquarks. And on the top right, I show the fit results from the fit step 3 and from the separate chi-square fit of the J-psi proton mass distribution. The compatibility with data here is poor, corresponding to the p-value of 10 to the minus 3. However, we have to test such fit against all possible systematics variations. And actually, the extended lambda star decay model that I just mentioned provide quite better description of the data. This yields the best agreement with data among all systematics variations, corresponding to the p-value of 9 10 to the minus 3. Which unfortunately does not allow us to exclude completely the decay model without pentaquarks. So this slide also shows some additional control plots for the nominal decay model and for the one without pentaquarks. You see that the description for the nominal model is slightly better, but as I said, does not allow us to exclude the no pentaquark hypothesis. Okay, so concluding, we have performed the study of the J-psi proton resonances in the lambda B decays with our run 1 data set. The model with 2 pentaquarks provides their parameters in good agreement with the result from LHCb. The model with 4 pentaquarks reported by LHCb later is equally consistent with our data, although independent measurement is too challenging yet. And although data prefer the model with pentaquarks, we still cannot exclude the hypothesis without pentaquarks within our statistical precision. Currently, we are working on the run 2 data analysis that will improve our results due to higher statistics, better mass resolution, and anticipated improvements in the procedure. Finally, I should say that also my talk included only the results on the pentaquarks. We have quite more studies on spectroscopy and exotic states in the pipeline. So stay tuned for new results from Atlas. Thank you.
Okay, thank you very much. Any comments or questions? Okay, so Marek.
Yes, Simeon, you mentioned this very briefly at the end. In addition to the pentaquarks from LHCb, there has been a very interesting result recently on dicharmonia. Can we expect something on that from Atlas and also perhaps on analogous states in the bottom sector?
Yes, indeed, we are aware of this result, and we are very keen at looking at this in Atlas. For dicharmonia, yes, I can confirm we are working on this. For dibottomonia, it's maybe a bit more complicated story, but yes, I totally agree. It would be interesting to have a look at this in Atlas too.
But not at this conference. You're not going to report anything on dicharmonia?
No, not yet.
Okay, thank you.
Okay, so the time is over. So Anton, please go to Mattermost chat to ask a question to Simeon. Okay, so let's move on to next talk. Thank you, Simeon. So next talk, Yixiong.
Okay, I'll try to share my screen.
Yes, please.
Can you see it?
Yes.
Okay, I will begin. And hi, everyone. Today I'm going to give a report about its charm-hadron property and the spectroscopy studies at LHCb on behalf of the LHCb collaborations. And okay, first a brief introduction about this LHCb experiment, and then some new results for this single and doubly charmed barons. And we know that LHCb, there's a huge amount of CC bar has been produced. The production cross-section is at a microbar level. And so far we have collected 9 investment bar data, which is corresponding to about 10 to the 13 CC bar events. But the reconstruction for this charmed hadron is rather challenging in LHCb, since we have this very high multiplicity. But LHCb's detector with this excellent vortexing and the PID performance, which offers us a great opportunity for this spectroscopy studies of the charmed barons. Okay, first some results for the single charmed barons. Then there's observation of this new excessive zero states. We know that we have shown in this previous HM meeting, there's the discovery for this 5 narrow omega-6 states. So following the same logic, we searched the new excessive zero resonance in this LHCb mass spectrum. And in this analysis, 2016 to 2018 data was used, which is taken at the central energy of 13 TeV and corresponding to 5.6 investment bar luminosity. And after all these selections, we have about 125 million LHCb candidates, and with a signal purity of 93%. As an illustration, red-hand plot showing the mass spectrum for this LHCb candidates. Okay, then we take a look at this LHCb mass spectrum. And in this feed, several feet down was considered, namely just some missing pion from some higher excessive states. And you can see from this plot, 3 clear peaks was observed. First 2 peaks are corresponding to new excessive states, which is observed for the first time and which very, very high significance. As for the third state, and its mass was very close to this well-known excessive zero 2970. However, its measured widths are quite different from these known states. Okay, then there's a lepton measurement of the 3 single-charm barons. We know that for the lepton, for the charm barons are very poorly measured compared to the charm mesons, but it's used to test this heavy Quark expansion series. And according to the theoretical expectations, the lepton hierarchy should be something like this. And the previous PDG results are consistent with the theoretical expectations. But as we've shown in this last HR meeting, LHCb has performed the lepton measurement for this omega-C barons, and it's about 268 femtoseconds, which is 3 times larger than this previous world average. So after updating this LHCb's results, the lepton hierarchy is completely changed. And to confirm such a new lepton hierarchy, we performed the lepton measurement for the 3 other single charm baron, namely the lambda C and KZC plus and KZC 0, and using the same method, which is through leptonic decays of these b-hadrons, and using the full run 1 data. And we have this larger statistics compared to any other previous measurement. And the lepton was measured relative to this D plus meson to reduce the systematics. And finally, the results are listed here. And as for the lambda C and the KZC plus, the results are consistent with previous world average. But however, for the KZC 0, there's a 3.3 sigma extension. And our results, the precision of our results are much improved compared to this superior PTG. And finally, we confirm this new lepton hierarchy. Okay, then there's an observation of this double capable surprise decays of KZC plus to P5. And we know that starting with this branching fraction ratio of the double capable surprise decay relative to capable favor decay can help us understand this non-spectacular quarks behaviors, and in particular this poly interference effect, which is crucial important for understanding this lepton hierarchy. So in this analysis, we are measuring the branching fraction ratio for this KZC plus decay to P5 relative to KZC plus decay to PK pi using 2012 data. And to subtract this P5 signal, we are performing this 2-dimensional fit on this PKK and KK mass spectrum. And the right-hand plot shows a projection of 1D projection for this PKK mass spectrum. You can see a clear signal peak was observed, and the significance is more than 50 sigma. And in this analysis, we even find some evidence for this non-fine contributions. And finally, this branch fraction ratios are measured to be about 2%. Okay, then there's a surprise decays for this KZC 0 to lambda C pi. We know for the decays of the KZC 0 is mainly proceeds through this decays of the charm quarks. But in this process, it can be proceed through this only through the S-quark decay or this weak scattering process. And measuring of this branch fraction can test the various of QCT models. And so in this analysis, we are measuring the branching fraction for this KZC 0 decay to lambda C pi, and also the KZC plus decay to PK pi using 2016 and 2018 data. And top red plot showing the mass spectrum from the lambda C pi, and you can see a clear signal peak observed. And the KZC 0 to lambda C pi was measured for the first time, and the results are listed here. And we also measure this branch fraction for KZC plus to PK pi, and the result is consistent with previous Bell's measurement, and which improved precision. Okay, then there are some results for this double charm barons. And we know that for the double charm baron, it was well predicted by the Quark model, and the red plot shows the SU for 20, and the one marked in red shows the 3 ground state charm barons. And according to this theoretical expectations, the mass of the KZCZ is about 3.6 GeV. As for this omega CZ is about 3.7. And for the lepton, as for the lepton, the singular charge CC plus and omega CC plus are expected to be much smaller than the double charge CC plus plus. And for this production cross section, this CC baron is are likely to be 3 or 4 times larger than this omega CC barons. And for this double charge K plus, it was observed by LHCb at 2017 with its decay to lambda k pi pi, and the mass was measured to be 3.621 GeV. And then using the same decay channel, the lepton was measured, and it's about 256 femtoseconds. And then it was confirmed by another decay channel, which is K plus decay to K plus pi plus. And this all been shown in these previous HR meetings. So after that, we also performed the search for K plus plus with its decay to dpk pi, but no evidence was found. So we set our upper limit on the branching fraction ratios relative to this observation channel, and it was a level of 10 to the minus 2. And then we also performed the mass measurement of the K plus plus using the 2016 to 2018 data. And both of the observed channel was used, and the lab plot shows the mass spectrum for these two decay channels, and the one marked in red showing the signal yields, so you can get roughly the idea how much statistics you got from these two decay channels. So by combining this, the results for these two channels, we have this so far the world's most accurate mass for this K plus plus, which is listed here. Okay, then we also performed the production measurement of the K plus plus using its decay to lambda k pi pi. We know for this K plus plus, the production mechanism is dominated by this gluon fusion, and the cross section in this LHCb acceptance is expected to be about 16 to 118 nanobar. And so in this analysis, we are measuring this production ratios for K plus plus relative to lambda c, using this 2016 data, and finally the measure to be at level 10 to the minus 4. Okay, last, then there's the search for the double charm baryon K plus. We know for the K plus it was cleaned by SELECT, but not confirmed by other experiments yet. So in LHCb, we search for the K plus through its decay to lambda k pi using the full run 1 and run 2 data. And but no evidence was found around the whole signal region. And then we do the local significance scan around the whole signal region, and the largest local significance is around the mass point of 3.72 GeV, which is very close to this K plus plus match point, which is observed by LHCb. But we taking into account this locale where in fact the global significance is only 1.7 sigma. So no evidence was found, so we set our limit on the production ratio relative to lambda c and K plus plus. And the bottom plot shows the upper limit results for this lambda c and K for the 13 TV examples. We are taking into account the different time hypotheses and mass hypotheses. And our results for the R lambda c is improved by 1 order of magnitude compared to the previous LHCb analysis. And the value is significantly below the one reported by SELECT. Okay, here comes to the summary. A lot of results in the charm sector was presented. First, there's an observation of the two new K0 states, and the left hand for these three single charm baryons measure with much improved precision. And then there's the observation of this very surprise decays of this K0 and the K plus decays. And we found K plus with decay to dpk pi, but no evidence was found. And also we can see that for the precision measurement of the K plus has already been started. And we also search for the single charge K plus LHCb, which much enlarged data sample, but still no evidence was found. And we will extend our search to different phenosids real soon. And after upgrade 1 or upgrade 2, we are approaching to the integrated luminosity to 15 and to 300 units femtobar. So in the very, I guess more results will be expected in the very near future. Okay, that's it. Thanks.
Thank you very much. Any comments or questions?
Yes, I wanted to ask a question, if I may.
Yes, please.
Okay. So, can you go back to the transparency about Xi plus and the look elsewhere issue?
Here?
Yeah, so the point is that look elsewhere is a statistical tool which is very important when you don't know what you're looking for. But since LHCb by now has established beyond any doubt the existence of Xi-CC++, isospin symmetry tells us that Xi-CC+ must be nearby. So the use of look elsewhere effect in this case is an overkill. It's not needed.
Yeah, but just to be conservative, since still there's no a clear observation of this classicity plus, and select such measure is way beyond this LCB's classicity plus match point. So just to be conservative, so we are giving.
But I think it's clear to everybody you need 5 sigma, etc. But in a way, LHCb in this case has been a little bit too modest, because it is clear that you are seeing the signal of Xi-CC+. It's just that it's only 3 sigma now, not 5 sigma.
Yes.
I think people should come out from your talk remembering that there is already a substantial indication. It's there. It is true, you have to wait for 5 sigma. Nevertheless, to say that you only have an upper bound is overdoing it a little bit.
Okay.
Okay, any other comment, questions? It seems not. Okay, thank you very much, Yixiong.
Okay.
Okay, so let's move on to the last talk in the session by Nikita.
Can you hear me?
Yes.
Good morning, everyone. Today I'm going to present you new results in lambda b baryon physics at CMS experiment. In this slide, you can see outline of my today talk. First of all, I want to introduce you CMS experiment. Then I will present study of excited lambda b baryons in lambda b pi pi final state. Then we will discuss observation of the lambda b to gypsy lambda phi decay, and then I will summarize up. In this slide, you can see CMS experiment. It consists of tracking system, hadron and electromagnetic calorimeter, superconducting solenoid, and the muon system. In lambda b studies, the tracking and muon systems plays the most important roles, because tracking systems allows us to reconstruct our tracks with high precision. For example, we measure PT with we measure PT very exactly, about 1%, and the muon system allows us to identify muons with very high precision. Now I'm going to present you study of excited lambda b states decaying to lambda b pi pi. First of all, in 2011, LHCb collaboration observed 2 narrow states in lambda b pi pi final state. They reconstructed lambda b into lambda c plus pi minus channel and reconstructed about 70,000 lambda b candidates. After combining with opposite charged pair of pions, they observed 2 clear peaks with significance more than 5 sigmas each and measured their masses, but then in CDF collaboration confirmed only the heavier state and with less significance. And recently LHCb collaboration observed 2 new excited states in lambda b pi pi final state in high mass region, and this time they reconstructed lambda b not only in lambda c plus pi minus channel, but in J psi proton k minus channel. And after combining with pions, they observed 2 peaks in lambda b pi pi invariant mass spectrum, measured their masses and natural widths. And right now, possible interpretation of such 2 states is a doublet of lambda b 1d states. And some theoretical background, we have a lot of theoretical predictions of excited lambda b and sigma b baryons. but the predicted masses are distributed in wide regions and don't point to any particular narrow window to search for a signal. But of course, some of them are in agreement with LHCb experiments, some of them don't, but it is often hard to say if they're in agreement with the measurement because they don't have uncertainties very often. Now we are moving to CMS study. CMS collaboration performed a study of excited lambda B baryons based on full run 2 data. In CMS, we unfortunately hasn't got any dedicated trigger for detection 3 tracks from one vertex and no hadron identifications. That's why we don't reconstruct lambda B in the lambda C plus pi minus channel, but we have got a flexible and efficient set of daemon triggers, and that's why we can reconstruct lambda B in Psi lambda and Psi 2s lambda final states, and we reconstructed about 46,000 of lambda B ground states. And after combining with opposite charged pair of pints, we can see 2 clear peaks with significance more than 5 sigmas, and it confirmed the LHCb measurement, and also mass measurement was performed. Now we are moving to high mass region in lambda B pi pi spectrum. And first of all, I want to pay your attention on mass 6150 MeV. And here we can see the structure with significance more than 5 sigmas. But as you can see, we cannot resolve it right now in 2 separate peaks. But anyway, we have our resolution from Monte Carlo. And LHCb collaboration measured the natural widths, and we can fix natural widths and resolutions, and after that can perform a measurement of these 2 lambda B excited states. But what is also interesting on this picture is that here we can see the broad structure, broad excess of events with local significance about 4 sigmas. And the mass measurement and width measurement was performed for it too. But nature of this white enhancement is still unclear. The structure disappears in same sign distribution, and you can see in the bottom pictures, blue data corresponds to same sign distributions. And also some correlation between this structure and sigma B and sigma B stars was indicated, and you can see in the central line pictures. Now I want to summarize up this study. The study was performed by CMS experiment and was confirmed for excited lambda B states, and mass measurement was performed too, and these masses are in a good agreement with LHCb measurements. And in addition, a broad structure was observed in mass region 6040 MeV, 6100 MeV, with local significance about 4 sigmas. But recently, LHCb collaboration performed their study on this mass region, and they confirmed existence of this broad structure with more statistical power. And right now, they interpreted it as lambda B 2s, first radial excitation of lambda B. Now we are moving to observation of the lambda B to Psi lambda phi decay. I want to start from history of B plus to Psi phi k plus studies. In 2008, CDF collaboration found an evidence of a narrow structure X4140 near the Psi phi threshold. After that, CMS collaboration observed this structure and also found an evidence of X4274. And finally, LHCb collaboration performed full amplitude analysis of these 4 and observed 4 exotic states. Our motivation is the next. We want better understand final state strong interactions in B baryon. Also, the lambda B to Psi lambda phi is a baryonic analogy of the B plus to Psi phi k plus decay, and detailed studies of Psi phi spectrum produced in baryonic decays may provide an important test for the production of observed exotic states. And finally, these decays will provide in future opportunity to investigate Psi lambda mass spectrum too, once a sufficient number of signal events is accumulated. Now we are moving to CMS study. This study was based on 2018 data with integrated luminosity about 60 reverse femtobarn. The left picture shows the invariant mass distribution of G lambda k plus k minus, and here we can see clear peak with significance more than 9 sigmas. But after that, we use a plot technique to obtain k plus k minus mass distribution from signal component, and finally we extracted the number of signal events lambda b to G lambda phi from by fitting this k plus k minus distribution. But with current statistics, it is not still possible to investigate G phi and G lambda spectra yet, because we have about 300 events total. Of course, it was chosen a normalization channel. It was lambda b to psi to s lambda, where psi to s we reconstructed in G pi pi mode, because it has this channel has absolutely the same topology as the main channel. And the invariant mass distribution you can see in the center of the slide. And of course, we measured the branching fraction ratio of these two decays according to this formula. And the value in the bottom of the slide was obtained. Now I want to summarize up my talk. Excited lambda b states are studied in the lambda b pi pi in CMS experiment. Also, existence of four excited lambda b states was confirmed, and the mass measurement was performed, and all these masses are in a good agreement with LHCb. Also, a broad excess of events was observed in the mass region 6040-6100 MeV, but we need, I think, more data for understanding the nature, and we are looking forward to run 3. And also, the observation of the lambda b to G lambda phi decay was performed, and we measured the branching fraction ratio of lambda b to G lambda phi and lambda b to psi to s lambda decays. Thank you for your attention.
Thank you very much. Any comments or questions? It seems not. Okay, so do you have a plan to extend the baryonic B analysis to sigma B or Xi B?
Yes, I think it is possible when we will have more statistics. But as I mentioned before, we haven't got too much signal events because we use GPSI. We use channels with GPSI in final state. But when we will have enough statistics, we can perform different studies for excited sigma B and other B baryons. And I think that some studies will be published soon.
Okay, thank you. Any other comments, questions? Okay, so thank you very much, Nikita. Thank you. Okay, so if you have a question to other speakers, please go to Mattermost. And let's thank all speakers in the session. And we will resume the next session from 10:07. So we have about 10 minutes coffee break.
Hello, can I test my audio? And
Oh, yes, you sound loud and clear. I can hear you very well.
okay, thanks. And I want to try to share to see.
That would be great, yes. And as is mentioned in the chat box, if anyone else who's presenting in this session wishes to test sharing their slides, please do so. So I see your slides very well, full screen, and can hear you well.
Okay, thanks a lot.
Hello everyone, I would like also to test.
Yes,
can you hear me?
Yes, I can hear you.
Okay.
Have you uploaded the slides to Indico, Eldar?
Not yet, just I will upload just after.
Okay, no problem. They look very nice. You can see them, and now in full screen.
Yes. Okay. Thank you.
Very good. Thank you.
Hello. Okay. Can I try also to share slides?
Yes, please do, Ivan.
Yeah.
Yep, very good.
Do you see them?
Yes, full screen, and they're moving nicely as well. Thank you.
Thank you. Yep.
Hello, can I try also?
Yes, please do, Wojciech. We see your slides also in full screen. They look very good. Beautiful, you might say.
Thank you.
No problem. Giulia, is it your turn to try?
Yeah, thanks.
Okay.
So, okay. So it's this one. And do you see in full screen yet already or not?
I'm not quite full screen yet. You can still see the top bar.
Okay, then now you.
And now this is full screen, yes.
Okay, thanks.
Thank you.
Hello, can I try to share my slide?
Yes, please do.
Okay. Can you see my slide?
Yes, we see them. They're full screen.
Okay.
Look very good. And we hear you well as well. And just a reminder to all the speakers, if you feel comfortable and if you have the bandwidth, please, you're encouraged to share your video while you're presenting, if you'd like to do so. It's not mandatory, but if you'd be interested and willing to do so, that would be nice.
Hi, may I also make a quick check?
Yes, of course, Florian.
Yeah, let me first try to share my video if this is working. Okay, and also my screen. Okay, is it full screen?
So we see you and your slides, yes.
Okay. I think there's this annoying green border, right?
Yeah, I think to solve this, if you make it full screen before sharing, it maybe
okay. Let me try that.
Avoids that. We can maybe just test this real time. Just
okay. So
maybe not.
I think it should be better now.
Yes, it's better. The green is still there to frame it, but it doesn't interfere with the slides at all. So
okay, perfect.
Fine. Yep, thank you.
Sorry, I have a quick question. Do you the mouse? I mean, the pointer is visible if we share the screen, right?
I believe your mouse pointer should be visible. Yep, I think so. You could just we still have a couple of minutes if you'd like to just confirm.
Let me try again, because if I maybe if I share, do you see the mouse or not moving?
I see it moving, yeah.
Okay, because
yep.
Just double check. Thanks.
Yeah, no problem.
Giulia, please don't
So
forget
Giulia,
to turn off your microphone.
I was just going to say the same thing. Thank you, Giulia. So, okay, maybe we should start getting prepared for the next session. We're only a minute or so away from starting. So the first person presenting here is going to be Peilian Li from LHCb on beauty to charmonuim decays at LHCb. So I'll stop my video and you're all shared. So just a reminder to all speakers that the talks are 12 minutes with 3 minutes for questions. And we'll put, if you seem to be a little slow, we'll put a word in the chat box with 2 minutes remaining. So the floor is yours, Peilian.
Okay, thanks. Can I start?
Yes, please.
Okay, good morning, everyone. Thanks a lot for listening my talk. I'm going to show you the latest results about the beauty to charmonuim decays and LHCb. And my talk will actually include the measurement of the time-dependent CP violation parameters phi, as well as a direct CP asymmetry measurement in B+2 gypsy rho plus decays. And as for other beauty to charmonuim decays, like the first isospin amplitude study could be found in Sheldon's talk on last Tuesday. So firstly, for the phi measurement, as we know, there are 3 different types of CP violation. One of them are the interference between the decay and the mixing. So BS is one of the good candidates to measure those kind of CP violation. As shown here, the BS could direct to the CP eigenstate directly. It could also oscillate to be BS bar and then decay to the same CP eigenstate. So as shown here, the diagram shows the leading contribution from the mixing and the direct decay from BS to gypsy hadron. And then here the phi is this mixing induced CP violation phase in the BS decays through B2 CC bar transitions. If we ignore the contribution from the penguin contribution, then the phi could be defined as shown here as the difference of the mixing weak phase, as the difference of the mixing phase, weak phase and the tree direct decay. And the penguin contribution is studied to be with a small shift around 1 millirad, which we expect to be much less than the statistic uncertainty of the phi, according to the previous study in the B02 gypsy 0 studies could be found in this reference. So it is safe to ignore the penguin contributions. And as we know, the phi is quite sensitive to the physics beyond the standard model, even at very high energy scales that might be inaccessible in the direct search. But the physics beyond the standard model could enter into the BS bar mixing, as shown in the diagrams here. So in this case, the phi could be redefined as shown in the box here. So And we know that in the standard model, assuming the unitarity of the CQ matrix, the global fit could give us a very precise prediction for the phi-s in the standard model as shown here. So if we could measure the phi-s experimentally and compare the measurements with the prediction, any deviation from this prediction could show us the evidence for the new physics. Then what we could do at LHCb, as you know, the LHCb has provided us a lot of B and BS candidates, which would give us the opportunity to measure the phi-s in BS2 gypsum hadron decays. As shown here is the detector of LHCb with the event display for the BS2 gypsum hadron. The BS could fly about 1 centimeter in the vertex detector and then decay to the gypsum hadron, and the 4 charge tracks could go through from the velo to track detector and the Gerick and calorimeters as shown here as the trajectory of the charge particles, and benefit with the excellent decay time resolution and the nice momentum resolution and the particle identification, which allows us to have a very clean BS2 gypsum hadron samples, and with a good tagging flavor tagging, we could apply a time-dependent measurement. In this talk, we will show you the results about the analysis for the data taken in 2015 and 2018. So let's have a look at the BS2 gypsum KK and the gypsum pi. The gypsum KK has relatively larger branching fractions, and its final state is a mixture of the CP even and CP odd components, which allows us to obtain the phi-s as well as the decay weights differences and the mass differences. Well, for gypsum pi, which has relatively lower branching fraction, is dominated by CP odd component. This allows us to measure the phi-s as well as the decay weights of the high eigenstates. The mass eigenstates could be expressed as a coupling of the Flavour eigenstates as shown here. We could parameterize the CP violation with the parameter of lambda, and the lambda is expected to be 1 within the standard model predictions of low CP violation. And in order to disentangle the CP even and CP odd final states, an angular analysis is required here. So to describe the distribution of the decay time and the angle, we defined the PDF as showing here, where include the function for the angular and the decay time. And to describe the angular function, we actually use the high-nicety formalism as showing here to show the 3 angles we used to define the angular function. And the time-dependent, the decay time resolution is also considered here by involving a Gaussian function, which take the decay time error per event as into account. And the flavor tagging would help us to take the flavor of BS and the production. So for the BS2 gypsum KK, we know which is dominated by gypsum phi, and in order to disentangle the contribution of the minor S wave, we divided the KK environments into 6 bins as shown here. Well, for the gypsum pi channel, since there's a lot of contribution from different resonances, we directly consider the contribution of the pi environment mass distribution into the final angular analysis into the final fate. So, and since we know that the gypsum pi is dominated by the CP odd contribution, so we fix the delta ms at the decay weights of light eigenstate to the previous studies, and we assume the same phi-s and lambda for all of the pi resonances. Then we fit to the 3 high-nicety angles and the BS candidates decay time for the gypsum KK with 1 more additional pi environment mass for the BS2 pi. And here is the fit results for gypsum KK and the pi respectively. As shown in the left side is for the gypsum KK, where you could see the contribution from CP even and CP odd components, as well as a minor contribution from the S wave. Well, for the gypsum pi channel, we found the CP odd contribution is greater than 97% and the 95% confidence level. And the two boxes here shows the fitted results for the phi-s, lambda, as well as decay weights. You could say all of them are consistent with each other. Well, by combining the latest results in round 2 with previous study in round 1, we could get the combined results and the LHCb as shown as in the upper plot where you could see the phi is still consistent with the standard model prediction with low CP violation. And the lambda is consistent with 1, which shows low direct CP violation as expected. And the ratio of gamma S over gamma D is consistent with the prediction as well. While combining the LHCb results with all the measurements from other experiments, we could get the latest world average value showing here, which you could see is dominated by LHCb's measurement. And the world average value is still consistent with standard model predictions. And here is also has a combination which considering the latest results from Atlas as shown in the left figure, where you could see the combined phi's and delta gamma S is consistent with the standard model prediction. But if you look at the right side, where include the measurement from the latest results from same as Atlas and LHCb, you could see some deviation in these 3 experiments, but all of them are still consistent with standard model. As we are still in progress with the full round 2 data, we hope we could have more precise measurements to help us to understand those possible deviations. And then let's go to the next topic about CP symmetry, direct CP symmetry in B+2 gypsy-rho. And B+2 gypsy-rho proceeds predominantly with the B2C transitions involving the tree and penguin amplitude that's showing in the diagram here. So the interference between these 2 amplitudes could lead to the direct CP violation. And experimentally, we could measure the CP symmetry according to the difference of the branching fractions that's showing in the formula here. Currently, we don't have the precise prediction for the CP symmetry of B+2 gypsy-rho, but we could expect it. We could estimate it assuming the isospin symmetry between the neutron and the charged B2 gypsy-rho decays. And the direct CP symmetry could also place the constraints on the penguin effects in the measurement of the phi's when we assume the SU3 flavor asymmetry and the neglecting the exchange and annihilation diagrams. So to extract the single events of the B+2 gypsy-rho, we actually applied the simultaneous 2D fate to the environment mass of gypsy pi plus and pi 0 and pi plus gamma gamma, as shown here with the 2011 and 12 data. And taking the B+2 gypsy key as a control channel, we could measure the branching fraction of B+2 gypsy-rho as shown with the formula showing here. And also the CP symmetry are measured, which shows no CP violation. And the results is still consistent with the measurement from the B02 gypsy-rho decays. Well, here brings me to my summary. In this talk, we show the latest time-dependent CP violation measurement for phi's in the BOT2 charmonuim decays, which you could see the world average results is still dominated by LHCb's measurement. And we also show the results about direct CP symmetry measurement for B+2 gypsy-rho, where those measurements could be helpful for us to place better constraint on the penguin contribution in phi's measurement. Well, with more measurements with full round 2 data and with more decay channels are in good progress, we hope we could have more precise measurement come out soon. And in the long term, as you could see in the plot here, we have an estimation about the the statistical uncertainty for the phi's measurement with the increasing luminosity in the upgrade for round 3, round 4, and round 5. And the round 3 is in good progress. We hope we could begin to take data in the coming year, and we will have about 23 integrated luminosity in round 3, which will help us to decrease the statistical uncertainty up to about 10 millirad. While with the integrated luminosity, this will also allow us to explore more decay modes and would also allow us to measure the independent CP violation effects in each polarization state. But with this, which would require us to have careful consideration for the penguin contribution, as well as the improved measurement for the B mixing and the lifetime. So stay tuned, and that's it. Thanks for your attention.
Thank you very much for the clear talk. We have time for some questions. Please either raise your hand or raise a question in the Mattermost. maybe I could ask a quick one on your projections going forward. Which are the systematics that will be dominating, and can these also be reduced as you integrate more luminosity?
You mean the systematic uncertainty?
Yes.
If I remember correctly, I think like the systematic uncertainty related to the angular acceptance and time acceptance might dominate. But I mean, in the long term, we also have the expectation about systematic uncertainty, but even for the run 3, we think the statistic uncertainty will still dominate.
Okay, good to know. Last chance for any further questions for the speaker. Seems it was a very clear talk, so we can thank you again, Peilian.
Thank you.
And we can thank you. We'll move on to the next talk. That's also LHCb from Wojciech Krupa, and now pivoting to beauty to open charm final states. We see your screen, and please you can start whenever you're ready.
Okay, can you see the slides?
Yes, and we hear you, and we see you. So please, whenever you're ready.
Okay. So good morning, everyone. My name is Wojciech Krupa, and I am working at AGH University of Science and Technology in Krakow. Today, on behalf of the LHCb collaboration, I will present very recent results of analysis beauty to open chart final state at LHCb. Undeniable, there is a huge potential of beauty to open chart processes in studies of the CK matrix parameter, including charge parity violation parameters, which can be probed especially using B2 decay processes, which I will mention since many results of these studies has been published recently, but today I will focus mainly on spectroscopy in the case of heavy mesons. Very briefly about the LHCb spectrometer, which is designed to study heavy flavor physics of particles which contain B and C quarks. On the slide has been highlighted the most important parameters of our detector as momentum decay time resolution and efficiency of our particle identification system. All of this allow us performing various studies with very high precision. There is also detector schematic with all main subsystem highlighted. Beauty to open charm processes family include the case of heavy B meson, but also other particles like lambda B, two different types of the D mesons, and combination of neutral and charge counts and pions. We present the results of 3 latest analyses at LHCb. Worth of notice is that the analysis of B0 to DS pi were approved 2 days ago, and results of analysis B0 to D0, D0 bar K pi were submitted to the journal 3 weeks ago. Here is also little other talks related to beauty to open charm decays during this conference. Yesterday were talks about time independent and time integrated measurements given by Evelina and Snaha. And so check YouTube and don't miss Daniel talk about exotic states, especially the results which he will present are correlated with this one which I'm going to present. So let's start with the B to D star decay studies. Basically, there's a long history of studies B to D star decays where B, D, and K can be neutral or charged meson. The first observation of processes from this family were published in 1997 and 1998 by the Clio and Aleph experiments. Then there were studies in 2003 and 2011, and now they are performed in the LHCb experiment. The LHCb performed measurement of relative branching fraction of decays listed on the slide. The control mode for these decays are basically be charge and neutral B meson decays to the decay system. We use full run 1 and run 2 9 invert femtobarn of data. These decays are especially interesting since they allow for the spectroscopy studies through their intermediate resonance structure. especially for the investigation of CS bar and CC bar structure via the D star D and D star K system. The specific topology of this decay allow for the strong suppression of combinatorial background in fully reconstructed decay chain. This feature makes them very good candidate for future amplitude analysis and LHCb, especially since only 2 amplitude analysis of processes from this family were performed till this day. And moreover, studies of these processes can provide important information about to calculation of the CC bar contribution above the open channel threshold in B2S LL processes such B0 to K star mu, which, as we know, are sensitive to the new physics beyond the standard model effects. As you can see on the slide, a large sample of B2 D star decays are available and can be isolated in the LHCb dataset with very low combinatorial background pollution. The feed to in the feed we use a double crystal ball function to model the signal and of course exponential function to model the background. And basically this is the standard approach in many analysis beauty to open channel processes at LHCb. On the slide, there are mass fit to the decay mode with the D star D bar D star decay modes for the run 1 and the run 2 data set, and here for the B2 DD bar K modes. And the branching fraction of this decay is proportional to the corrected using also selection efficiency, acceptance efficiency, and more. On the plot, you can see those efficiencies as a function of positioning the two bodies squared invariant mass plane for all decay modes. Those efficiencies are calculated separately for the round 1 and round 2 data set. And on the slide, you can see the efficiency for the round 2 data sample. Since we calculate the relative branching fraction, many of uncertainties are cancelled, but other which arise from the shape of the model which we are using, efficiency of the selection, efficiency of identification, as well as other sources are taken into account. The relative branching fraction of all decays are on the slide, and with the control modes which has been used in the measurement. And there are results with the systematic, statistical, and uncertainties which comes from the analysis of the control mode. We got very good consistency with previous results from other experiments with excellent precision of our measurement, which comes from it. We stick to B2DDK and B2DDK5 family of processes. This is very new result of D0 to D0 D0 bar K5 analysis. We study processes with B2 CC bar S bar transition. Results of this analysis also CC bar input to the K star mu analysis, and this is very good opportunity to search new excited CC bar and CS state, especially like C4260 or tetra quark candidate Z4430, which both decay to D star D and D star K system. This is branching fraction measurement, which is calculated using branching fraction on the control mode B0 to D star D0K. Efficiency for total efficiency for both the modes and number of candidates for both modes. Worthwhile notice is that again mass distribution is very clear, especially for the control mode. As you can see, the number of candidates, there is also the number of candidates used in both measurement, as you can see, is relatively low. On the slide, there are results of measurement of branching fraction, relative branching fraction in reference to the control mode, and the total branching fraction. These three plots show the background subtracted invariant mass distribution of pair D0, D0, D0K, and K5, all from the D0 meson decay, including efficiency effects derived from the simulation. So as you can see, there are hints of structures D0 at these masses, like C3770, DS2 star 2573, DS103 star 2860 and K star 1892 on the first, second, and third plot respectively. But care should be taken with any interpretation of this projection because they can be a reflection. So basically, further studies are required. At the end, very fresh results from branching fraction measurement of the B0 to DS5 decay. These studies allow to measure 5 physical observables. Firstly is relative branching fraction in reference to control mode B0 to D5. Then we have the branching fraction of B0 to DS5 decay. We measure also the ratio between Habibo suppressed D plus pi minus mode and favored D minus pi plus mode. This ratio is necessary in charge parity asymmetry measurement for this decay. To check why it's so important, watch Evelina talk about time-dependent measurements. And this decay proceeds through a single amplitude involving B2U transition. And since then, this result can provide information on non-factorizable strong interaction effect, quantified as ANF, or the magnitude of the CK matrix element VUB. The ANF indicates how much D as mesons interact with the pion through the strong force. These studies are especially interesting since the ANF parameter is basically unknown, and there is no good theoretical prediction. All-inclusive and inclusive VUB prediction are done with the assumption that the ANF is equal 1. Finally, studies of difference in the production ratio of the BS and B0 mesons, called FS to FD ratio, and at the different energies. This value is crucial for studies of all BS decays at LHCb, especially like BS to mu. The value of this ratio show correlation with the energy of collision, which was also measured in the studies. And the branching fraction, how we calculate the formula for the branching fraction is on the slide. Basically, the VUB and VCS is the CK matrix amplitude of CK matrix elements. F is the form factor, FDS is the DS decay constant, and ANF quantifies non-factorizable effects. Since the VCS is well determined, this parameter as well as the form factor of decay constant is taken as input, and since then the branching fraction can be used to measure the product of VUB ANF, or one of these two elements if the second one is taken as an input. On the left, the mass fit to the control mode B2 D5 with the highlighted contribution of the signal, a combinatorial background, and partially reconstructed background. And here for the same variant mass distribution for the signal mode of the DS part. And on the right, there's a result of measurement of product ANF VUB in comparison with average, inclusive, and exclusive prediction of this for these elements, with all of them with naive on the naive factorization equal as unity. There is which you can compare with our measurement, and there is also result of collision energy dependency with naive linearity. And to sum up, many updated results and many new results from studies beauty token processes at LHCb. Still, there is a huge potential of new such as new, more complicated processes with more resonant states and with more particular final state. And now all results have good agreement with the standard model prediction and are excellent input to the further studies of resonance states at LHCb. Expected integrated luminosity collected during run 3 and run 4 is very good prospect for the further studies, future studies. So stay tuned for more to come, and thank you for attention.
Okay, thank you very much for the clear talk. We have time for a couple of questions if people have something to ask. I don't see any hands raised or anything in the chat window. all very clear. One last chance to raise your hands for questions to Wojciech. No? Okay, it was a very clear talk then. Thank you very much. That was very nice. And we can move on to the next presentation, which will be from Florian Reiss, on the study of b-hadron properties with semileptonic b-hadron decays.
Okay, can you see the slides?
We see the slides, we see you.
Okay, perfect.
And I think whenever you're ready, you can get started.
Okay, thanks. So hi everybody. So I would like to tell you about the study of b-hadron properties using semileptonic decays at LHCb. So just to briefly motivate why this is interesting. So using semileptonic decays, we have, of course, large branch infractions and in turn small statistical uncertainties, and also the theoretical uncertainties are under control since we have only one hadronic current, which we can parameterize by form factors. Also, there are a couple of very interesting observations in the we saw with semileptonic B decays. So, for example, the tension between the exclusive and inclusive determination of VCB or Lepton universality test, and measuring the properties of b-hadrons can help us understand them better. So, and LHCb is a very suitable place to make this measurement since we have a detector with a trigger designed for triggering on those displaced b-hadron decays, and we have a large sample recorded, including BS, BC, and lambda B. The results I would like to cover are the measurements of b-hadron partition fractions, then the observation of the decay B plus to a proton, antiproton, and the mu nu, and finally the shape of the BS to ds star mu nu differential decay rate. So starting with b-hadron partition fractions. So what we want to measure in this publication is the BS and lambda B protection fractions relative to that of the sum of B minus and B0 using data recorded at 13 TeV, while we have a measurement at 7 TeV already performed some time ago. This is motivated by the fact that we need to know those protection fractions to determine absolute protection fractions from BS or lambda B. The strategy we follow here is that we perform the measurement in bins of the transverse momentum and pseudo-rapidity of the b-hadron, since the production fraction might depend on it. And the assumption going into it is that the semileptonic width of the various b-hadrons is almost the same with small corrections taken into account from this paper. To obtain the yield of the b-hadrons, we use the inclusive b-hadron to c-hadron mu nu decays. The c-hadron are ds, lambda c, the 0 or d plus. And then what you need to do is to determine the efficiency and branch infraction corrected yields, which then leads us to our results. So what we see is that we have no dependence of the relative production fraction on the pseudo-rapidity of the b-hadron, but we have a dependence on the transverse momentum as shown on the right, where you can see the lambda b and BS production fractions as function of the BT of the b-hadron, where we have a strong dependence in case of the lambda b and the slight one in case of the BS. Then moving on to a related measurement of the BC production fraction at 7 and 13 TeV. So here we reconstruct the BC and the decay chip psi muon neutrino. Now the assumption that the semileptonic width is the same of the BC compared to the other Bs is not given anymore. So instead we rely on an average of predictions for the BC to chip psi mu partition fraction. And we extract the BC yield by fitting the so-called corrected mass, which depends on the shape size mu invariant mass and also the transverse momentum component of the BC with respect to its direction of flight. And on the bottom, you can see those fits to the corrected mass at 7 TeV and 13 TeV on the left and right, with the orange component and showing the signal contribution. And again, we check for dependence on eta and PT, and we see no dependence on eta, and the slight one on PT as shown here for 7 and 13 TeV. Moving on to the observation of the B+ to proton, antiproton, muon, neutrino. So this search is motivated that we have those RD and RD star anomalies, and we would also like to perform similar measurements using B quark to U quark transitions, and detecting decays like this would be a first step. Also, we have predictions by Petrov with QCD for the absolute pressure fraction of this decay, which we then can test, and also there's evidence from Belle that this decay might actually take place. So what you use here is to use data recorded at 7, 8, and 13 TeV at LHCb, where we measure the pressure fraction in bins of the proton and antiproton invariant mass. Again, we extract the signal yields by fitting the corrected mass, and we use then the B+ to chip size K as a normalization channel, where the chip size decays to a mu plus, mu minus, to then obtain the absolute pressure fraction using the known B+ to chip size K+ pressure fraction. Here you can see the fits performed to extract the signal yields in the different proton, antiproton invariant mass bands, with the signal contribution shown as dotted black line, where we combine the whole data sample to increase the fit stability. Which then leads us to a result of the absolute pressure fraction of the B+ to proton antiproton mu decay, which is lower than the theory prediction. However, if we compare the shape of the theoretical prediction with the data, it's consistent. This is shown here, where we see the differential pressure fraction as function of the proton antiproton invariant mass, with the measured values in black and the theory prediction in red, where the absolute or the overall scale of the theory is scaled to the observed value, and you can see the shape increase. And also we observe this threshold enhancement effect at lower values of the proton invariant mass. Now, finally going to the measurement of the shape of the BS to DS star mu nu differential decay rate. So this measurement is motivated by the fact that we see this discrepancy between the inclusive and exclusive determination of VCB, and since the exclusive determination relies on form factors, measuring the form factors can help clear up this picture. Also, measuring these form factors provide an input for theoretical calculations of, for example, an DS star ratio, which we then can also measure to perform a Lepton universality test. And what is good about this decay is that we have a heavy spectator S quark, which leads to more precise theory predictions. So the two form factor models which parameterize the hadronic currents are the commonly used CNN and BGL parameterizations. And what we now first need to do is to obtain the efficiency corrected yields in bins of the hadron we call W, which is related to the lepton neutrino invariant mass square Q square. We use data recorded in 2016 at 13 TeV, and we reconstruct the DS star in the decay to a DS and the photon, where on the bottom right you can see the DS gamma invariant mass with a broad peak corresponding to the DS star. Then we extract the signal yields in bins of W by performing a template fit to the corrected mass, which is shown here, where the signal contribution is the big red one. And finally, we can perform a form factor fit by fitting the unfolded and efficiency corrected W distribution with the corresponding form factor models. The result of which is shown here, where you can see the unfolded W distribution as black points, and the fit with the BGL parameterization in orange, and the fit with the CLN parameterization in green. And as you can see, they both parameterizations are consistent with each other, and also with the data. So this already brings me to my conclusion. So we can measure many properties of b-hadron at LHCb, as I showed you, for example, the relative production fractions of BS, lambda b, and BC. You can make first observations of B to U quark transitions to perform universality tests there in the future. And we also have the first time measurement of the unfold normalized differential decay rate of the BS to DS star mu decay. And these properties are then important input for theory and experiment, as I try to demonstrate. So we have production fraction measurements which we need for absolute branching ratios. We can test projections of perturbative QSD, and also we can measure form factors to get more precise RX predictions used in Lepton universality tests. So yeah, that's all I wanted to show. So thanks a lot for your attention. And are there any questions?
Thank you, Florian. We have time for questions, as the speaker says. Please raise your hand. Or just speak up. Maybe I could start with a quick one on your slide 15. Your differential distributions versus MPP bar. Have you looked at these also versus any of the angular predictions from the theory papers as well? I think there's if I recall, an angular distribution, and maybe the mu nu mass as well. Have these also been checked?
I have to double check, but as far as I'm aware, we have not.
Could be a useful cross check as well, but this is already very convincing as a distribution. Are there any further questions? Don't see anything in the chat window. And no hands are being raised. So very clear once again. Okay, one last chance. No. Okay. Thank you, Florian.
Thank you.
And we can move on to the next speaker.
Yeah.
And next up we have Lupato presenting new results on semileptonic and leptonic b-meson decays from the Belle experiment.
Can you see my screen?
Yes, I see it very well, and we see you and hear you very well.
Okay,
so,
great.
Perfect. The floor is yours.
Okay, so I'm going to present our new results on the inclusive B2XU1 new decays from Belle experiment. Okay. So as you know, we can study the second matrix measurement from the Semileptonic decay. Depends on what kind of in vivo states you are looking on. Then we can determine the VUB either by exclusive channels or fully inclusive channels. But we saw the VUB puzzle from you will comparing the VUB, determine the VUB values by these two different methods. Or so there is about 3 sigma tension in between. So this is called a VUB puzzle. Another part for this motivation is the VUB measurement in this inclusive way is quite challenging because the high dome background is super high coming from the second favored B2XL new decays. As you can see on the right side, we illustrate the invariant mass spectrum for X system and also the lepton momentum in B-rest frame by also scanning up on the B2CL new part. Will scan down by a factor of 50 to show them for B2U side by side. As you can find, the background is super high, and one can only get very clear separation for the B2U and B2C. Is only looking at certain phase-space regions, for example, the low MX region or at the endpoint of the lepton spectrum.
Okay, I'm going to show you a very short overview on our reconstruction strategy. We used the full data set from Belle I, which is about 711 investigator bar. And we starting from E plus E minus collection, and there is U7 for a state generated, and it decays to a pair of BB bar. And 1B is used at the target site, which is fully reconstructed by its hadronic decays based on neural networks. And the efficiency is about 0.3 to 0.2%. On the other side, we have signal B, and we choose the lepton, which has a relatively high energy, and the rest of event, whatever left in the event, we reconstructed as a hadronic system called XU. Since we have fully reconstructed the Decays site, it gives us a chance to reconstruct the hadronic system by doing this ways to sum up all of the charged particles and also all of the energies deposited on the electron calorimeter. So in this way, we can fully reconstruct the full momentum for the hadronic system and also calculate the meson mass squared by using the full momentum conservation from the initial state from E plus E minus collection. And also we can calculate the lepton system information, for example, the Q-square distributions. So these are the important kinematic variables we're going to use in our analysis strategies and also the final results. Okay, let's show you how we suppress the B2C background. We use the boosted distribution trees called BDT to suppress our high B2C background. As I show you on the top left is the BDT classifies output comparing data and monocolor together. So the high background coming from B2C showing in blue, and our signal in red is quite tiny on the bottom. And we applied arbitrary factor to just show you the illustration of the shape of the signal in dashed red colored lines here. And in addition to this BDT classifier scores, we also show you the top ranking input features variables, for example, the meson mass squared, and also the vertex space between the lepton and other pions in the event. And all of them shows a very good data and MC agreement. Okay, this is our distributions before we cut on our BDT. So it's kind of combining the B2C and B2U together. And all of them have illustrate that with full monocolor uncertainties, and also we separate the B2C background by different type of X system like B2D, B2D star, and D double star, and so on. And for all of them, we can see that our signal B2XU is super tiny. Luckily, after BDT cut, we can see some signal much more visible in these distributions. By doing cut BDT at around 0.83, we get roughly about 30% signal left, and we removed about 98% background, which is quite efficient. Okay, let's move on to our signal extraction. We eventually fit the signals in the following 3 different phase space regions. The first one is with the lepton in the BRS difference larger than 1 GeV, which gave us about 86% of the full accessible phase space region of B2 XU and decays. The second one with additional MX cut, MX smaller than 1.7 GeV, is combining these two, we have about 56% of phase space. And the last one is with additional Q-square cut and Q-square larger than 8 GeV squared. So in this case, we can access about 31% with the from the full phase space regions. With these 3 different phase space regions, we either fit the lepton spectra or MX or Q-square, or combined MX and Q-square in the 2D fit, as summarized in the tables below. And for most of them, we have 3 templates to extract the signals and also define the signal out, which is events, our signal events, but for outside the phase space cut. And last template is the background, which combines the remaining B2C after BDT cut and also the continuum and secondary and fake lepton events. So eventually we carry out these 5 different phases. And for the electron phase, we can also compare that with the different other phases with identical phase-space region. So the EL phase we use as a cross-check. Okay, I will show you the results. First one is for the phase-space region with lepton spectral higher than 1 GeV and MX lower than 1.7 GeV. We fit this region with 2 different variables. The left one is with MX. As you see here, the pool distribution shows the phasor converge very well. And also on your right hand is we fit the EL spectrum. Since this 2 is coming from the same phase-space region, we expect the branching fraction from these 2 should be compatible, and this is actually what we saw here. This is our preliminary determination for the partial branch fraction in these phase-space regions, and this is also compatible with the past Baba analysis results. And this one is with our 2D phase. I show you the projection on the MX and on the left and the Q-square distribution on the right hand. With this 2D phase, we access the region, phase-space region with the EL larger than 1 GeV. And here we get the partial branch fraction in this space region with this 1.56 times 10 to the minus 3 as this partial branch fraction. And comparing to the past, is also acceptable, compatible together with uncertainties. With the obtained partial branch fraction, we can determine the VUB values by taking the average B meson lifetime and also the theoretical prediction for the decay rates for the different phase-space regions. And we use the following 4 state-of-the-art theory predictions. They are BLNP, DGE, and GGOU and ADFR. So these are the predicted decay rates we used for the following 3 different phase-space regions, which are identical with the heavy flavor average group used in the latest VUB determinations. Okay, this table summarizes all of the preliminary results on our VUB values for different various phases in different phase-space region and also for different theoretical input. And we found the most precise one is coming from 2D phase, combining MX and Q-square phase. And we also, this one also covers the largest phase-space region. So our final results will cite this 2D phase result. In order to double check our extracted VUB as a different size of the background, we choose 2 more BDT working point cuts to compare the VUB values. As you can see here, by cut looser or tighter, we can also increase or reduce our background by this portion. And our extracted VUB somehow remains quite stable as illustrated by this figure. And the range of the shift of the VUB is about from minus 0.2% to 1.2%, which is quite stable. So by doing this, we take the arithmetic average of all the results for the different theory calculations. Our average VUB is determined in this as these values as preliminary results. The central value is 4.06 times 10 to the minus 3. And we compare our inclusive average values to other variables, for example, the heavy flavor average for B2 pioneer decays, these exclusive channels. And we found the tension is about 1.4 sigma. And if we compare to the global fit result from second filter, the tension is about 1.6 sigma. Let's look back to the VUB values over the time being. So the blue dot here shows you the result coming from inclusive determinations from over past BTG second review. And the orange dot shows you the exclusive measurements results. And in the recent 5 years, we also have some input from the leptonic decays and baryon from LHCb channels. And our result here with the Belle preliminary point, we indicate the purple cross here, which actually getting closer to the exclusive determinations on VUB. Okay. Yeah, this brings me to my last slide for summary. We studied the hadronic takt analysis with full Belle I data set, and we present our preliminary results for the partial binding fraction in the phase-space region with lepton spectral larger than 1 GeV, and based on that, we extracted the VUB to about 4.606 times 10 to minus 3. The measured partial binding fractions for various phase-space regions are compatible with all of the previous Belle and also BABA results. And the VUB we extracted based on this partial binding fraction shows a tension between the exclusive channels and inclusive measurements. It's about 1.4 standard deviations. Yeah, that's all from my side. Thank you.
Okay, thank you very much for this clear and, of course, very interesting talk. We do have time for some questions, so please raise your hand or speak up if you have a question or a comment. Very nice to see the summary of VUB as a function of time and your slide 14 and how the results are evolving. Of course, this has been a long-standing puzzle, so it's interesting to see where your work sits here, just bringing the inclusive and exclusive results closer together. We'll see where this goes in the next few years. Final chance for questions to the speaker. Seems we have a lot of very clear talks today. So thank you very much again. That's very nice presentation, and we can move on to the next talk.
Yes.
Excuse me, I've muted. So yes, the next talk will be Sanqiang Qu from the BEST 3 collaboration, talking us through semileptonic and leptonic charm decays at BEST 3. So please, whenever you're ready, you can start your presentation.
Okay, thank you. So I'm very happy to be here and give you a talk about the semileptonic and the leptonic charm decay at the BEST 3. And this is my outline. First of all, I will give a brief introduction to the leptonic and semileptonic charm decays experimental method and the data set at the BEST 3. After that, I'm going to show the recent results from the leptonic and semileptonic charm decay from the BEST 3. And eventually, I will give a summary. Okay, now let's get started. Here is the brief introduction to the leptonic and semileptonic charm decays. The left and the right figure shows the Freeman diagram of the leptonic and semileptonic charm decays. Based on this formula, we can see if we have a decay width or the differential decay rate and input the CKM matrix elements VCD or the VCS, we can get the decay constant or the form factors, which can calibrate the theoretical calculations. Inversely, if we input the decay constant or the form factor of the DS or D to P, and we can see we can obtain the CKM matrix elements VCS or the VCD, which can test the unitary of the CKM matrix and search for the new physics beyond the standard model. As we know that we also can test on the flavor, Lepton Flavour universalities in the charm section if we determine the ratio of the decay width of the D or DS decay to the different flavor lepton. Here is the BPC2 and the battery detector, which are located in the Institute of High Energy Physics in Beijing. This slide shows some more information for the battery detectors. Here, I won't go into more detail because this plot seems as the previously battery presentation. So here is the experimental method and the data set at the battery. In the battery, we used the double tag method to measure the absolute branching fraction of the leptonic and semileptonic charm decays, as shown in the Formula 3. And we all know that the battery cannot detect the neutrino, so we defined the kinematic variables of the missing neutrino as the U-miss or the missing mass square. By fitting the U-miss or the missing mass square distribution, we can obtain the signal use of the leptonic and the semileptonic charm decays. And the red plot shows the data set at the battery. After that, I'm going to show the recent result from the battery. And here is the result of the D plus goes to the tau neutrino and the DS plus goes to the mu neutrino. And the left figure shows the fitting of the missing mass square for these two decay channels. For the D plus goes to the tau neutrino, we can see we measured the branching fraction for the first time with a significance of the 5.1 sigma. And we also determined the ratio of the decay width of D plus goes to the tau neutrino and D plus goes to the mu neutrino. And the result is shown here, and we can see it is consistent with standard model predictions. For the DS goes to the mu neutrino, we measured the branching fractions, the decay constant of DS, and we also determined the ratio of the decay width, and this number is consistent with the standard model prediction. Here is the comparison of the decay constant of the D plus and the DS plus. By inputting the secant matrix elements VCD or the VCS from the secant filter calibration, and we can obtain the results of the decay constant of D and DS. So in this plot, the blue one shows the battery results. For the semileptonic decay at the battery, I'm going to show the D0 goes to the K mu neutrino. And this plot shows the fitting of the U-miss distribution or the differential decay rate and the form factor in the each Q square bin. And we measured the branching fractions and the form factor of the D to K. And we can get the ratio of the branching fraction for this value. We can see it is consistent with the standard model predictions. This slide shows the result of the D plus goes to the eta mu neutrino, and although it was predicted by the Quark model in the 1989, but this is the first time to measure the branching fractions for this channel. And we also get the form factor of the D to eta, and the ratio of the branching fraction are be determined. So here is the comparison of the form factor of D to pi and D to K. And in this plot, the blue shows the battery result. And for the DS leptonic charm decays, I'm going to show the DS goes to the eta or eta prime in neutrino. And this plot shows the fitting of the missing mass square and the form factor in each Q square bin. And we also list the results from these two decay channel. And we also measured the form factor for the first time, and the form factor of the DS to the eta or DS to the eta prime show listed here. For this channel, we also list the comparison of the ds goes to the for factor of the ds goes to the eta, or ds goes to the eta prime, as shown in the left figure. And this figure shows the comparison of the eta and the eta prime missing angle, which can be determined by this formula. And if we input the branching fractions of the d plus go to the eta or eta prime e neutrino in the previously battery result, the eta missing angle phi can be determined by the 40.1 degrees. So here is the comparison of the secant matrix elements VCD and the VCS. If we input the for factor and the decay constant, we can get the result of the secant matrix elements VCD or the VCS. And so in this plot, the blue shows the battery result. And for another semileptonic charm decay as the battery, and we shows the d plus goes to the omega mu neutrino, and the ds goes to the phi e neutrino, and the phi goes to the k plus k minus. For the d plus goes to the omega mu neutrino, it was the first time to measure the branching fraction, although it was predicted by the Quark model in the 1989. For the ds goes to the phi e neutrino, and this plot shows the projection of the data and the PW fitting for the 5 kinematic variables. By the PW fitting, we obtained the 604 events. And according to the distribution of the cosine theta k, we can see there's no observed the significance from the F0918 or the phase space SV. So this slide shows the result of the ds goes to the K0 in neutrino and the K star 0 in neutrino. And we also list the result of the branching fractions. And in this channel, we measure the for factor of the ds to the K0 for the first time. So this slide shows the d goes to the pi e neutrino, and in this decay channel, we observed the SV contributions for the first time, and we determined the components of the SV, and we also measured the branching fraction of this decay channel. And according to the branching fraction, we can calculate the ratio of this, and we can see the ratio of the branching fraction is larger than 2.7. And our result indicated that the quadro-quark description favored for this 3 decay channel. This slide shows the result of the d plus goes to the K10 in neutrino. For this decay channel, we measured the branching fractions for the result listed here, and we found that the significance are larger than the 10 sigma. For the K1 missing angle theta K1, our result indicated that if the theta K1 equals 33 degrees or the 57 degrees, our results are agrees with the theoretical predictions. Okay, this is a summary. Recently, the battery has studied a lot of the leptonic and semileptonic decays. We divided them roughly into the 6 categories. For the test the Lepton Flavour universalities, we can see there's no evidence for the Lepton Flavour universalities violation in the charm at the 1.5%. Actually, by using the data at the 4119 to the 4230, more DS leptonic and semileptonic charm decays are being studied. And based on the data taking proposal in the battery, in the next 2 years, we will collect the more precise double prime data. So in the future, more results from battery to be expected. So that's all. Thank you for listening.
Thank you very much for this nice and comprehensive overview of exciting results at BEST 3. We have time for some questions. I see Doris already has a hand raised. So please, Doris.
I'm interested in one of your conclusions that you think that the resonance at the light hadron, such as A0 and F0, favors tetraquark interpretation. So tetraquark means there are 4 quarks. So which flavor are you talking about?
I think it's UDCS. So the printer or the UUDDS, I think so.
Oh, I see. UUDDS. Yeah. Okay. Thank you.
Okay, thank you for that question, Doris. I see it's interesting that your RD and RDS measurements from the D to tau and D to mu seem to be in agreement with the standard model predictions. We still have time for some additional questions if people have more questions or clarifications about these exciting BEST 3 results. Last chance. Well, once again, let's thank the speaker. And if anything else comes up or people have additional thoughts or questions to ask the speakers, just a reminder that we're using the Mattermost channel and people should feel free to ask additional questions if they think of something later on in the session or in a future session. So thank you very much for this talk.
Okay, thank you.
We'll move on to the next speaker, who I think is Eldar Ganiev. Eldar, are you there?
Yes.
Yes, we see you and your nice slides. So if you could make these full screen, that's great.
Okay.
And you're ready to take over whenever you'd like to start. Thank you.
Okay, thank you. So hello everyone. Today I would like to present you results on early charmless BDK physics in Belle II experiment. So just to remind you, charmless BDKs have no charm quark in the final state. They are mediated by Kabibah suppressed B2U quark or loop suppressed B2D and B2S quark transition. The first charmless signal was observed by Cleo collaboration in 1993. And now charmless impact roughly account for about 15% of all experimental flavor physics papers coming from LHCb and B factories. So why charmless is so attractive? Charmless BDKs are highly sensitive to the presence of new particles in the loops. They allow to probe non-standard model dynamics in each of the 3 CKM angles. And also they provide valuable information to constrain theoretical models of BDKs. But they are quite challenging to study due to their low branching fraction of order 10 to the minus 5 or less, and also due to the fact that the final state can be easily mimicked by many backgrounds. So the study of charmless decays is a keystone of Belle II physics program. And given good performance of central drift chamber, vertex detector, particle identification systems, and electromagnetic colorimeter, Belle II can enable advances such as reaching about 1.5 degree precision on alpha phi 2 CKM angle. provide a conclusive understanding of so-called K-pi puzzle, searching for local CP asymmetries and three-body decays, and also measure time-dependent CP violation with B0 to phi K-short decay mode. Belle II complements LHCb experiment. It mostly advances in studies of channels with neutral particles and K-short mesons. Belle II started its operation with all the detectors installed and operational in 2019. And up to now, it has collected about 75 inverse femtobarn of data. Moreover, Super KKB Collider achieved world record luminosity with currents lower than those that were used at KKB. And all this achievement boosted many activities in the physics groups in Belle II. So, and today I will present the first measurements of branching fraction, CP asymmetry, and polarization for charmless B decays using 35 inverse femtobarn of Y4S data. So everyone, please welcome charmless 12. Now I will lead you through the main steps of the analysis. So first we need to separate peers from apples, namely continuum events from BB bar events. Then we need to optimize the selection to enrich sample in signal events. Then we calculate efficiency based on the signal Monte Carlo simulation. Then to extract the signal for 8 of the channels, we perform one-dimensional fit of delta E distribution, where delta E is a difference between reconstructed B candidate energy and known beam energy. And for 4 channels, we do a multidimensional fit. So then we measure branching fraction, finally, and CP asymmetries and longitudinal polarization, and assess for possible systematic effects. The main challenge of this analysis is to reject the dominant background which is coming from production of light quark pairs, continuum. In E plus, E minus to hadron collisions, only each fifth collision produce a BB pair. And then given the low branching fraction of charmless decays, it's almost impossible to see the signal without treating a continuum background. So for this, we exploit a topological difference between a continuum event, which usually has a cigar-like shape, and BB pair event, and B event, which has a more spherical shape. So we combine non-linearly many kinematic decay time and topology variables to maximize signal to background ratio. And then for each channel, we optimize the selection using simulated and control sample data. Hence, we obtain we obtain a continuum suppression selection efficiency in range from 35 to 79% for various charmless channel, while rejecting 96 to 99% of continuum background. And this ROC curve, you can see that our continuum suppression improved in comparison to the first charmless signal result which we presented in Belle II Beauty conference. Okay, let's move to the interesting part. First, we'll discuss about branching fractions. So here's the results for B0 to K plus pi minus and B0 to pi plus pi minus decay modes, which are very useful to probe tracking and particle identification performance. So from the fit of the delta E distribution, we obtain about 290 B0 to K plus pi minus decay, and we measure the branching fraction, which is in a good agreement with world average value. The same was performed for B0 to pi plus pi minus decay, and the branching fraction is in a good agreement with the world average. Also here you can see that we can quite well distinguish the peak coming, signal peak coming from B0 to pi plus pi minus decay and B0 to k plus pi minus decay, which help to assess the PID performance. Now let's move to the channels with the pi 0 in the final state. So we managed to measure a branching fraction of B plus to k plus pi 0 decay, and the result is in a good agreement with the world average. Also, we achieved the first reconstruction of B plus to pi plus pi 0 decay in Belle II data. And this result is also consistent with the world average. Now the channels with k short in the final state. So by fitting to the B plus to k short pi plus data sample, we obtained 65 signal events, and that allow us to measure a branching fraction of B plus to k0 pi plus, which is in a good agreement with the world average. Also, we managed to reconstruct B0 to k short pi 0 decay, which is essential for the inquiry isospin sum rule, and the result is in a good agreement with the world average as well. So now three-body decays, which has more rich intermediate structure and many peaking backgrounds. So we managed to measure branching fraction of B plus to k plus pi minus pi plus, which is consistent with the world average, and B plus to k plus k minus k plus, which is also shows a good result here. Also, we measured CP asymmetries in two-body decays. So for this, we did a simultaneous fit of positive and negative B samples. And we measured CP asymmetries for B0 to k plus pi minus, B plus to k short pi plus, B plus to k plus pi 0, and B plus to pi plus pi 0 decay modes. And all the results are consistent with the world average. And also we managed to measure CP asymmetries in three-body decays. They also show very good results with respect to the world average one. So now let's move to more advanced analysis. So first, the analysis of B2 vector and pseudo-scalar mesons, and B plus to phi k plus and B0 to phi k0 decays. So here we performed a 5-dimensional fit, and with 55 signal events, we managed to measure branching fraction, which is consistent with the world average. And also the same applied for the B0 to phi K0 decay mode, which also shows good result with comparison to world average. And these two decays were first time reconstructed in Belle II data. Now B2 two-vector meson decays, which require full angular analysis. So these are decays of B plus to phi K star plus and B0 to phi K star 0. So here we did a 7-dimensional fit, and we, apart from measuring branching fraction, we also measured the fraction of longitudinally polarized B decays. And both results for both the channels are consistent with the world average. And of course, all the results presented today, they're preliminary and they require more work, but we're already happy that that we have a good consistency with the world average, and that performance of the detector and the reconstruction tools is quite good. So to summarize, presented the first measurements of branching fraction, CPS symmetries, and polarization in charmless BDKs with 35 inverse femtobarn of epsilon4s data. Results are in a good agreement with world average values, and performance is comparable with Belle performance. So we can ensure that we have a good understanding of detector and tools. And Belle II is on track to explore non-standard model indications in quark dynamics. So that was it. Thank you for your attention.
Thank you very much, Eldar, for this really comprehensive study of the charmless 12, as you call them, and yes, the very exciting prospects for Belle II into the future. We have time for questions if people wanted to raise their hand or just write something in the chat box. Any questions or comments? I also don't see anything coming up on the Mattermost chat related to the talk. Are there prospects to improve the systematics for many of these channels, or are there particular systematics maybe related to the neutral pions that would need some work to be able to improve things?
Oh, we surely will improve the systematics. Now the uncertainty dominated by statistics. So of course, when we hit the systematic border, we will improve systematics, of course, and we will work on it now already.
Yes, I imagine with the ramp up of data collection at Belle II, that would be reasonably quick to reach this limit where you need to improve the systematics as well. In some of the channels, the statistics are already competing with the systematic effects. So again, last chance for questions. This very nice talk. I don't see any, so thank you once again, Eldar. That was very nice, very clear.
Thank you.
And we'll move on to the next presentation, and that's Giulia Casarosa, telling us about the charm potential of Belle II.
Okay, can you hear me? I hope.
We can hear you. We see your slides, and if you could just make them full screen, if that's possible. There we go. That's great. So please, whenever you're ready, you can start.
Okay, so let me tell you about the charm potential at Belle II. I will start telling you where we are with the experiment, and then I will show you the prospects for charm measurements at 15 Borsato barn, which is the data set that we plan to collect in the next years. I'll also show you some plots that show the current reconstruction performances of the experiment, and I will touch these things here, so mixing and CP evaluation, and then what we can do with a full charm event reconstruction. So you already heard from the previous talk, but we started data taking with the full detector last year, and we collected roughly 75 inverse femtobarn, most of them in 2020. Let me underline that the worldwide emergency that we're living did not stop the operations of the detector and the accelerator. And as a matter of fact, the Super KKB achieved the world record luminosity in June with 2.4 10 to the 34 centimeters square per second. So clearly the data set is not at the level of Belle Babar, but it is extremely useful to check the reconstruction performance, the resolution, and the systematics effects, because we have to keep in mind that the physics measurements will benefit from the increased statistics if we can get resolution which is comparable or even better than Belle, and also if the systematic uncertainty is reduced too. So let me show you the prospects. These are basically extrapolations based on Belle analysis and simulations. They are all in the Belle II physics book. And there is a main assumption which is shown in this formula here, that most of the systematics scale with the statistics. So we scale it with the luminosity. And then there is a part of the systematics which we do not scale, we just add in quadrature. As I said, I also show you some plots with the current performances of the detector to show you where we are. So let's start with CP evaluation. So time integrated CP asymmetries. This is the mass peak of the D0 to K short candidates that I will comment better later. So let's start with this big table that reports the many channels in which Belle has measured CP asymmetries with the luminosity that they used and also the value of the CP asymmetry that was extracted. And in the last column, you see the expected total error from Belle from 15 Borsato bar. So you see that we can measure CP asymmetry in several channels. This is needed to overcome the difficulties in the computation of the standard model prediction that need some help, let's say, from the experimental side. So for example, one can use the sum rules. You can estimate the SU3 flavor symmetry breaking effects. For this, you need CP asymmetries and branching ratios of channels that are connected by the symmetry. So for example, the 0 to KK and the 0 to pi pi channels are connected to the D0 to pi 0 channel. So it's important to measure CP asymmetry also here. ML2 will for sure contribute in measuring CP asymmetries in channels with neutrals in the final state and reach also precision of the order of 10 to the minus 4 in some of these channels. So let me show you that we can, that we do see the 0 to K short, and the 0 to K short by 0 in our data set. You see them in the bigger plots in the middle of the slide. On the left, you have the D-star tagged the 0 to K short delta M candidates, the delta M distribution. And on the right, the D0 to K short by 0. And just for a qualitative comparison with Belle, I've reported also the plot from the similar plot, let's say, from Belle analysis on the edges of the slide. And you see that there is a very good performance of the reconstruction of Belle II, which is approaching Belle performance after just 1.5 years of data taking. And of course, there is still room for improvements for us to improve everything, the reconstruction, the calibration, and everything. So in this slide, I want to show you that we reconstruct also neutrals. For example, the pi 0 in a gamma final state, or the eta in the same final state, the eta also in the 3 pi 0 final state. We do have lambda c reconstructing the pk pi final state on the bottom left, and not just the 0, but also the sub s. So the top right plot shows the d sub s to phi pi, and the bottom the d sub s to k short k. Okay, now let's move to mixing and CP evaluation. I'll actually start with some kind of bonus, let's say, slides, bonus measurements, which is the D0 lifetime, because this measurement represents a full checkup of the detector and of the reconstruction performance, of the experiment. So we do reconstruct the D0 meson tagged from the star decay in 3 signal channels. We have D0 to K pi, D0 to K pi pi 0, and D0 to K3 pi. And then we fit the proper time distribution with the ambient maximum likelihood fit using per candidate proper time errors. And on the bottom, you see the 3 plots that show the projections on the proper time of this fit and the lifetimes that have been extracted using a luminosity of around 10 inverse femtobarn. So there is a summary plot on the right where you see the 3 measurements that are all compatible with one another. We also take the average of these measurements, and we find for 12.3 plus or minus 2 femtosecond, which is perfectly in agreement with the world average. And let me underline that with just 10 inverse femton, our statistical error, even though it's only statistical, it starts to be comparable with the world average error on the lifetime of the D0. Now, if you have done some charm analysis in Belle or Babar, you may have noticed this from the previous slide, but this slide show is much better. So we do have proper time resolution at Belle II, which is a factor 2 better than Belle and Babar, and this is thanks to our vertex detector. So this is, I hope, clear from the right plot that you see. I've superimposed the proper time distribution for D0 to K pi final states for a channel reconstructed by these 3 experiments. So the Belle resolution, let's say, it's visible at negative proper times in the blue line. Then we have Babar in black, and then we have Belle in red. And you see that the Belle resolution, the Belle II resolution is much narrower with respect to the previous experiment. So this is an improvement thanks to the detector, and of course it has an impact also on the time-dependent measurement, in particular when we want to measure mixing and CP ovulation observables. So in order to get an estimate of the improvement that we will get with this better resolution, we did some toy Monte Carlo. We looked at the wrong sign d0 to kpi analysis, which is almost systematically free. So it's the best thing for this kind of estimation. And we scaled the Belle errors to 15 per Satobar, and you see the numbers here. And then we took the PDF from Belle, we plugged in the better proper time resolution, and we also simulated 15 per Satobar, and we get this precision on the mixing parameters. So for example, if you look at Y prime, you see that we expect from Belle, let's say, scaling to 15 per Satobar 0.16%, but with improved proper time resolution, we do even better. We can get to 0.10%. So this is to show that thanks to a better detector, we expect to achieve precision that goes beyond the increase of luminosity that we will get. So let me show you that we also see wrong sign D0 decays. So on the right, you see the D0 to the wrong sign decay of the D0 to K3 pi, K pi pi 0, and K pi. We reconstruct right sign and wrong sign, and then we extract the yields of the wrong sign using the PDF that we have fitted from the right sign, and you see that it can perfectly describe the wrong sign distributions. This is the delta M distribution. Then to check that everything is under control, we also computed the ratio of wrong sign to right sign of the yields that we have extracted, and this is expected to be equivalent to the ratio of the branching ratios if everything is under control, and we do actually observe this, and this is shown in this bottom plot. Now let's go to the golden channel D0 to K-short pi analysis. This is golden because it allows to do a direct measurement of the mixing and CP ovulation parameters. So the previous B-factory, Babar and Belle, have done this measurement with a time-dependent fit to the Dalitz amplitudes, assuming a model for the Dalitz and extracting the amplitudes and phases of the model from the data. So if you assume a model, of course, this is a source of what we call irreducible systematics. And but we have this information at the moment. So what we can do to get the precision that we can expect at Belle II is to scale the errors that we have in the Belle analysis. And this clearly does not include the improved proper time resolution that I was mentioning before. So if you look at the bottom table, you have for each block here, the first line represents the error that Belle have extracted, the statistical, then the systematical, reducible and irreducible, and then the total, and then how we scale them to 5 and 15 Versatomer. So you see that with the 5 in Versatomer, but for sure for 15 Versatomer, we will, if we use exactly the same method, then we will be limited by this irreducible systematic. So for this, we have to change the measurement, let's say, and do something different than what is done by Babar and Belle, and probably LHCb is already doing something different. So there are many options, let's say. On the right, you see the D0 to K-short pi candidates that we have in our data set. Actually, in the 2019 data set, you have the Q distribution on the top and the mass distribution on the bottom, and you see this is very, very clean with very small background. There is a sensitivity study which is ongoing for mixing and CP ovulation parameters. This is the Dalitz plot. And to double check again, we extracted also the lifetime for this channel, which is 4.8 plus or minus 5. So this is, again, compatible with world average. And also the resolution is compatible with what we have observed in the lifetime analysis, and roughly a factor 2 better than Belle, as observed in other channels. So the last topic is the full charm event reconstruction. So this is basically a method that was used by Belle, and you see the bottom plot here, which is called recoil method, used for the analysis of the leptonic decays of the Sabes, and it consists in reconstructing everything, let's say, from the CC bar event. So there will be a D, which is going to decay in the signal channel. The other charm, Quark, hadronizes in some other D mesons or baryons, and we reconstruct it in as many channels as possible. And then we also reconstruct the fragmentation, which is basically consisting in light mesons. Then, for example, if you think about the leptonic decay, of course, the neutrino is not visible. So we use the energy and momentum conservation to search for it, basically, by computing these missing quantities of using everything that the things that we have observed in the events and computing the missing mass square. So for this channel, the missing mass is the mass of the neutrino. And for the signal, it peaks at 0, and the background is somewhere else. So this is a very useful technique that, of course, we can use to do the same thing. So to look at the leptonic decays of the Sabes to mu or the d to mu. For example, if we scale the Belle measurements to 15 Borsato bar, we expect to have errors on BCS and FD sub S, which are order of 1/3 of the theory error. So this would be very nice. And with 15 Borsato bar, we can also look at the D plus to mu, which is not visible at Belle or Babar because of the statistics. And now if we scale the simulation that we have in Belle, then we expect to be competitive with Clio C and BES3 for this channel. Now, this technique can also be used to reconstruct an inclusive sample of, for example, here we have D0 or lambda C, using basically the same technique, apart from the fact that now the missing mass is the mass of the meson or the baryon that you want to reconstruct inclusively. In Belle, this analysis has been used to look for D0 to invisible, and here you have an example. And we can also use it for lambda C, but this is, again, an example. This is some results on simulation. And if we compute what we expect with 15 Borsato bar, we see that we expect around 40 millions inclusive D0 at 15 Borsato bar and around almost 3 millions inclusive lambda C. So these are unique samples that allow us to search, for example, for rare and forbidden decays with missing energy in the final states. Of course, this also works for semileptonic decays, but I guess there is no more time. So let me conclude. I hope that I convinced you that Belle II potential in many charm measurement is big, at least on paper, let's say, so extrapolating from Belle. But now we're doing the steps of confirming this with the data, looking at the reconstruction performance, for example, which is improving with time, and in many cases it's comparable, or even better. For example, this is a clear example, or better than Belle II. So stay tuned for many results on charm that will come from Belle II in the next year. Thanks for your attention.
Thank you very much, Giulia, for a very clear and exciting talk. We do have time for some questions if people have some. Please either just raise your hand or type something in the chat box. We're checking the Mattermost as well, but I don't see anything coming up there. You mentioned on the previous slide that this technique, which is obviously very exciting, could also be used for semileptonic decays. Is this something that's been demonstrated previously, or something that people are working on within Belle II?
Well, we are surely working on that in Belle II. I think it was also done in Belle. Now I don't recall exactly. I can provide you the answer in the Mattermost channel.
Okay, thank you. And can this technique also be applied to the d sub s to tau nu? Is that something possible to do, or are there?
Yeah, it's possible.
That should be okay with this.
Yeah, with two neutrinos, it will be a little bit more complicated. The missing mass will be less straightforward. Let's say that. Yes. Sorry, I didn't meant to do that. To interpret the plot is probably not peaking exactly at 0. So
yes,
we can try.
Okay, thank you. Last chance for any further questions to Giulia. Very exciting times for charm physics at Belle II, so we'll look forward to these results in the next few years. Thank you very much for the clear talk, and we'll move on to the final presentation of this session. That is by Ivan Lukashenko.
Good morning. I Do you see the
Ivan.
presentation?
We do. We see your slides and we can hear you very well.
Great.
So, and we see you as well. Perfect.
Okay, great.
The triple threat. Okay, so whenever you're ready, you can take the floor and we'll listen to your talk. Thank you.
Good afternoon, I guess. Let me present some results from CMD3 detector. At CMD3, we study hadron production in E plus or minus annihilation at low energies, low energies meaning below 2 GeV. This energy region is interesting. This data is used to study properties of light vector mesons, which are produced directly in a plus or minus, or other light mesons, which can be found in various intermediate states, and in general to understand how hadronization occurs in this non-perturbative region. But certainly the most known application of this data is related to muon G-2. These data, plus minus hadrons at low energies, gives the key, is a key experimental input for calculation of the hadronic contribution to muon G-2. As you're well aware, there is a long-standing about 4 sigma deviation between Brookhaven result and standard model calculation, and we eagerly waiting for new result from Fermilab, which should confirm and improve the Brookhaven result. And this data is important to reduce error on standard model calculation. Web 2000 is the only machine which is can directly access this low energy range, and it also is accessed at flavor factories at Babar, and now plan to done at Belle II and at Chloe via ISR method, where the hadronic system is studied together with ISR gamma. Web 2000 is located at Novosibirsk. It's a relatively small plus or minus collider, single bunch mode. Design luminosity is 10 to the 32 at the highest energy. There are 2 experiments running at the collider, CMD3 and SND. I will talk about CMD3, SND, they will be talked tomorrow. It's important to mention that we continuously monitor energy of the beam using Compton backscattering during the data taking. That's important for some precision measurements. After the initial 3 years of running, we had 3 or slightly more years upgrade, where the Web 2000 was connected to big injection complex in the institute that allows us to raise luminosity by a factor of 5 or so. We even surpassed design luminosity in the middle energies. Detectors resumed data taking in 2017 and continue on. Well, not right now, but in general, we're taking data. Most of the data was collected over a couple last years, but most of the published results are based on the initial data. Certainly, just now. This is how it looks like. CMD3 is a general detector, more or less standard design for E plus and minus. There is a central drift chamber, which is surrounded by electromagnetic calorimeter, and there are muon counters outside. The unusual part is that in the barrel part, the electromagnetic calorimeter made of 2 kind of super layers. Inner one is made of liquid xenon, and outer one from cesium crystals. And between these 2, there are time of flight counters. The liquid xenon calorimeter has several layers inside, and it has strip structure, which allows us to measure the profile of the shower. It's important for, we use it for particle ID, and also it has a good resolution for conversion point for gammas. So in general, we have like 100 micron tracking, 3 to 10% energy resolution, and about half a nanosecond timing in TOF counters. Over the years, we took data in the whole energy range of up to 1,000. We have data, we had scans, wide energy range scans were kind of dedicated to measure cross sections in the whole range. And also I had dedicated runs where we put larger integrals at a particular interesting points. Well, in our case, these are several resonances, and especially large chunk of data above pp bar NN bar production threshold, where things become different. And I'll talk about this later. At Web 2000 at CMD3, we do exclusive measurement of plus or minus 2 hadrons, which meaning we study each final state one by one. There are, in this energy range, there are about a couple dozens of final states which we can access. The red ones are where the results were published. With more data, we probably reiterate these results, but in principle, some results were published. And blue, where the analysis is ongoing. This is the ontology of the published results. It doesn't make any sense to go one by one. There are, each of them has some different history. This is overall picture of the cross sections measured. You can see that they span several orders of magnitude, and that's probably about, I don't know, quarter of what we plan to measure during the whole duration of experiment. Let me focus on the couple very recent results, which were just published in 2020. One is K-short by plus by minus. These final states with 2 kinds and 2 pines, there are several of them with different combinations of neutrals and charged. They're not, only a few of them are measured. So in general, this channel is not very well measured. And that's a first direct measurement of this channel. Before it was only measured in ISR in one experiment. We reached about 10% systematic uncertainty and showed that the mechanism is K-star, main mechanism for this decay. Also, we recently published much more kind of important cross-section in terms of it gives a larger contribution to the total cross-section, eta pi plus pi minus. We reached about 6% systematic uncertainty, showed that it's dominated by eta rho. For the rest of the talk, let me switch only to the ongoing analysis and preliminary results not published. The most expected and probably most interesting result from CMD3 will be measurement of the plus minus to pi plus pi minus. It's a most simple hadronic channel that's most challenging because here the high precision is a requirement. This channel alone is responsible for about 70% of the hadronic contribution to muon G-2, and to match expected precision of the Fermilab, final precision of the Fermilab measurement, this channel should be measured to about 0.25%. Right now, there are already several measurements of this channel, high precision measurements with precision better than 1%. But in comparison, there are discrepancies between these measurements, several percent discrepancies. So this channel, it's very important to have another high precision measurement on the next level. For CMD3, it originally was it was one of the main goals for the experiment, so the detector was optimized for this measurement. We already performed several scans of the whole energy range, and in particular the raw region of the raw meson, where the contribution from this channel is the largest. And in analysis, we do two separate analyses of the same channel to have a cross checks using either momentum or energy deposition of the particles, or now developing where we do classifiers and then use classifiers output as an input to the analysis. Overall goal is to reach about 0.5% systematics, and with other experiments that will bring us to this 0.25%. let me skip this one. We basically closing into the end of the analysis. This shows it's a blinded picture, but it shows basically how the result looks like. And also that we have two independent methods which overlap in the main part of the interesting part of the result. At high energies, we have only one method of analysis. We have a very good agreement between results obtained for different energy scans, which were taken at very different times and with very different detector. The statistical precision which we reach is way better than available right now. These blue bars is a statistical precision of CMD3 and other statistical precisions of other experiments. So you see it's factor of 2 or more improvement in sigma. And right now the expected systematic is 0.6% at raw, and there is these red ones is where we have some room for improvement. So we continue to try to push the systematic down. Let me now switch to different topic. In the whole energy range of Web 2000, there is one interesting point: PP bar and N bar production production threshold. And Web 2000 has a unique opportunity to carefully study this production region, to scan it with small energy steps. We did one of the scans. We plan to do more with high statistics. But with the first scan, we observed interesting phenomena like very sharp increase of the PP bar cross-section and sharp drop in other cross-section like 6 pi's charged or K plus K minus pi plus pi minus. The width of this increases or drops is very narrow, about 1 MeV, which is consistent with the energy resolution. So we don't really know the width. We know it's very small. And there is puzzling that for some channels, which you would expect to be coupled to PP bar as much as 6 pi's, for example, there is no corresponding drop. So there is no good model for that. And we plan to do a comprehensive study of this energy range. For multi-hadron final states, the intermediate dynamics could be complicated. There could be several intermediate particles, mesons. To improve the precision, we can do combined analysis of several final states. And for example, for pi's, we do simultaneous unbinned likelihood fit of more than 100,000 of 4 pi events together, neutral mode with 2 pi zeros and all charged. Simultaneous fit. The amplitudes, intermediate amplitudes taken into account, there are several of them, and this is a preliminary result of such amplitude analysis. And the final topic is, it's a bit off topic for CMD3, but it's very relevant for this parallel session, is a search for a plus or minus to d star 0. The idea is to, instead of searching for ray decay d star 0 to plus or minus, to search for d star 0 in production, and plus or minus goes to d star 0. The mass of d star 0 is just at the edge of Web 2000, so it's Web 2000 running up to 2000 MeV, but we were able to slightly increase the upper energy and collected data at d star 0. The idea was proposed in this paper, and this particular decay d star 0 to plus or minus is interesting because it's a powerful test for new physics. The standard model contribution is very suppressed, but in some new physics models, the effect could be quite large. So for analysis, we use d star decay to K3 pi all charged. With the data we collected, we obtained upper limit 1.7 10 to the minus 6. It's certainly far from the interesting region, but that's a first result. There was no this upper limit before. And interesting to mention that in original paper, the original estimations were much more optimistic, because in the paper, the detection efficiency was underestimated, I mean, overestimated. But realistically, we have about what we could do is about 1%. And also, there was missing factor, which accounts for energy spread and plus or minus collider. And that's a big suppression factor, another big suppression factor. At Web 2000, we can probably reach 10 to the minus 7, taking more data, but that's quite reasonable to take like 100 picobars of this energy. At best 3, probably with dedicated running and one inverse femtobarn, it's possible to reach something like 10 to the minus 8 to the minus 9. But to reach the interesting range, like 10 to the minus 11, the much larger integral is required, like 100 inverse femtobarns, which will be possible only at future proposed supercharged tau factor next generation after best 3. Let me stop here. At CMD3, we collected about 300 inverse picobarn in this low energy range. And overall, we plan to collect about 1 inverse femtobarn. And also, I should mention that we plan to upgrade detector and install additional systems, which will allow to increase accuracy for multi-hadron states. Thank you.
Thank you, Ivan. Very interesting, exciting times. We have time for maybe a quick question, if someone has one. Yes, Anton, please go ahead.
Hi, Ivan. So maybe I'm missing something, but I mean, why don't you measure E plus or minus to D0, but D star 0?
It's helicity suppressed. D0, D star is vector. It can be directly produced. D0 yes. Cannot be produced directly.
No, but I mean, you're still looking for new physics, right? So I mean, it could be some new physics signal if you see E plus or minus to D0. So I think it makes sense to also put the upper limit on this.
Okay, that's something to think about. Okay, yeah, I didn't think about that. Mm-hmm.
Okay, so you have a additional analysis to be doing. You know? Time for one additional quick comment or question. Thank you for that, Anton. If not, I guess we can thank you, Ivan, for this clear and interesting presentation, and thank all of the speakers in the session. I think this has been very interesting, a lot of very clear talks, and I think we can take that away. If there's any further questions, we can follow that up on the Mattermost, but for now we get a short coffee break before the session continues. So thank you all very much. Bye.
Also, as usual, we encourage people to try their setups during the coffee break. The next speakers, if they want to, unless they have tested it already before.
Hello.
Yeah. Hello.
I'm Lupato.
Yep. Hello. Hi. So I can hear you well. Do you want to try to share?
Yeah, thank you.
Yes, I can see it quite clear in full screen without any.
Thank you.
Yeah, thanks.
Hello.
Oh.
Can you hear me?
Yeah, we can hear well.
Okay, so my name is Michał Siderski. I'm the second speaker.
Yes.
So maybe I could also try to share the screen so you can see.
Yeah, go ahead.
Okay.
Okay.
Can you see now?
Yes, now we can see it full screen again without any issues. It's fine.
Okay, nice. So I will then hide my screen.
Yeah.
This is okay. You share now. Pause the share now. Stop. Okay, thanks. Sorry.
Yeah,
and video. Oh, you can see me probably.
Yeah, I can see you.
Okay. Good. Nice. Thanks.
Hello?
Hello, Giulia. Yeah,
Hello?
I can hear you.
Okay, perfect. Can I try also the sharing?
Sure.
Okay, thank you. Let's see. So are you seeing it in?
Yes, I see that there's this green border, which
okay.
I believe, yeah, I think you just need to go full screen first and then share to make it, but it's not too distracting, so you can.
Okay, so I will just try if I'm able to. So if I do it now, you see, so, okay.
Okay, the green border is still there, but
yes,
I think it's fine. It doesn't matter much.
Hello.
Hello, Nikita.
Yes, I also want to try the
sure.
sharing. Yes. Okay. So, can you see the slides?
Yes. Maybe can you try to go full screen just to?
Okay. Now.
Yes, it is there.
Okay. So I'll try to on the video.
Yeah, it seems to work. Yeah, there is again this green band, but I don't think that there is a way to easily get around with this. As I know that there should be possibility to remove it by firstly going to full screen and then try to share. But yeah, I'm not quite sure if it will work easily.
Okay, you can see me now, right?
Yes, we can see you.
Okay. Okay, thanks. I'll just stop.
Hello.
Hello.
So I'm Anton, the next speaker.
Hello, Anton.
Yeah, should I already start sharing my slides, or you want to show something?
Maybe. Well, maybe you can. We should start again according to the agenda at 12:14, which is basically a minute.
Yeah. No,
just to make sure.
Just to save some time. Okay.
Yeah, but go ahead. Yeah, start sharing the introduction slide from you.
Okay. So let me write this. Yeah, and then again, can you see it okay now?
Yeah, I can see it. There is again this green band. Yeah. How can we do this? Okay, it's not, well, it's a little bit over. I don't know, do you see the green band as well? Probably not.
I do see it.
Yeah. Okay.
But I'm not sure how to get rid of it. So.
There is a hint in the chat.
Yeah.
Okay.
Yeah, that's what we are trying, I guess.
Yeah, I'm not sure I can
very
see the chat while I'm sharing the slides.
Yeah.
Let me try to see. Okay, go full screen first, but then once I go full screen, how do I press the share button? Okay, let me try.
Yeah, right. Alt tab to switch to your Zoom from the full screen. Well, the full screen.
Is it visible now?
No, it doesn't look like you are sharing anything.
Okay. Interesting. Yes.
Yeah, it is better now. At least
Okay.
at least in the sense that the green box is not over the slides.
Okay,
it's now around them, so it's fine.
Okay, great.
Okay, so I think we can start. We are already on time. So as I understood, Anton, you are going to tell us about possibility how to search for invisible particles in BS oscillations. So please go ahead.
Yes, exactly. So I would like to present here the kind of a new experimental technique to search for the decays with the invisible particles using the b-sub-s oscillation. So this is the presentation based on our recent publication with Adam Morris, who is also here, I guess. So, well, as you have seen in the previous talks, there are a lot of interesting measurements that could be done with the decays of B mesons, where you have some invisible particles in the final states. Of course, mostly it's semileptonic decays, but also you can imagine like hadronic decays with neutrons or K-longs, or even some new physics candidates like heavy neutrinos, axion-like particles, or other dark matter candidates. So in E plus or minus machines, we have a nice technique that we can use the kinematic constraints, because we have only BB bar produced without any additional particles. So we can reconstruct one of the B mesons fully, and then we can constrain the form momentum of the probe B, the other B, so that we can kinematically just calculate the needed constraints. But with the hadron machines, the problem is that there are no such a kinematic constraint. So what we are doing in the current analysis is we're using topology of the B decays to constrain at least the direction of flight of the B, but there is no constraint on the momentum, on the absolute value of the momentum. So, and this is clearly not sufficient. For instance, if you are searching for some decays where the mass of a heavy invisible particle is unknown, or if you have more than one neutrino and so on. And in general, this also gives a large background from the other b-hadron decays. And this is basically what we are going to overcome by using this technique, where we use b-sub-s oscillations pattern to obtain the additional kinematic constraint. So we have tested this technique well in Monte Carlo basically so far with the simplest case, where our b-sub-s decays into the AX combination, where A is fully reconstructed and X is invisible, and possibly with the unknown mass. So as a nice example of the new physics model, which could benefit from these techniques, is, for instance, this publication here, where you have both baryon asymmetry and dark matter explained from in the CP evaluation in the B meson oscillations, and with the subsequent decays into the dark matter particles. And one of the standard model benchmark analysis could be, for instance, B sub S to D sub S proton anti-neutron, where you expect a sufficiently large branching ratio just from the open charm final state. So of course, we mostly aiming for LHCb, but probably this could be also done with other hadronic machines in the future, or Atlas and CMS. Depending on their ability to tag the flavor of the bee. So while I'm showing the results with the massive invisible particle, this could be applied also to the final states with the unreconstructed particles of with the massless final states, for instance, semileptonic. So the idea is that so you can see here a nice pattern of the B sub S oscillations as measured LHCb, and this is a very specific pattern that we have very fast flavor oscillations. This is the unique system. All the other neutral particles are oscillating quite much slower, and this could help. I mean, if we see this pattern in our decay, we can efficiently remove any non-B sub S background, and we can also constrain the momentum of the B, because the time and the vertex displacement x are related by this equation, as you can see here. Of course, we cannot reconstruct well, we don't know the momentum of the B once we have the invisible particle, but we can reconstruct the momentum taking the topology of the event. So if we know the decay position of the B sub S and the direction of flight of this reconstructed A particle, we can just from the kinematics we have two solutions for the PB for the absolute value of the B momentum, which are given by this rather complicated formula, and this plot here shows the example of how the two solutions are. What kind of two solutions you get for each particular value of the angle between the B sub S and A, which can be reconstructed from the vertices as a function of the momentum of the particle A that is fully reconstructed. So then you can use this momentum PB from the topology, and you can take some probe mass m small x to see if you see basically the oscillations. So what I'm showing here is based on the simulation how the B sub S decay time distribution depends on this probe mass mx for the two solutions for this minimum and maximum PB solutions as shown by the formula in the previous slide. And you can see that this reconstructed decay time it depends on the value of this probe mass. And for the correct probe mass, where mx is equals to the true mass, we obtain the frequency of oscillations, which is matching the known frequency of the B sub S oscillations. We know that PB minimum provides better oscillation pattern, so it more often gives the right solution. So in the following, we just use this one solution here. And instead of the absolute rates, it's convenient to use the flavor asymmetry as defined here. So this is the number of mixed and unmixed, the difference between the number of mixed and unmixed B sub S's divided by the sum. And so this is the asymmetry that is defined from -1 to 1. And you can again see this asymmetry as a function of the probe mass x and the B decay time. And this plot here shows the oscillations of this asymmetry for 3 different probe masses. The correct one is 1 GeV, and also the probe masses of 0 and 2 GeV. So you can see that for the correct mass, the amplitude of the oscillation is maximal, and the frequency of the oscillations is the correct one, the one that you expect for the B sub-S's. So this is showing you somehow the animation of how the analysis could be done, right? So you're basically trying different probe masses, and at some point you will see that the oscillations are at the right frequency. So this is pretty much the same as like rotating the tuning knob on the old-fashioned radio, right? So at some point you will hear your favorite broadcasting on the radio station. Okay, so instead of just looking at this this oscillation frequency as a function of decay time, you can just present this in the Fourier transformed way, right? So you can look at the amplitude of the harmonic at the B sub S oscillation frequency. So this is a complex number. So you have this C and S, the cosine and sine term of the corresponding harmonic. And those 2 plots show you how this cosine and sine term depend on the probe mass X for different true masses. So as you can see that C, the cosine term reaches maximum at the correct mass, and the S term crosses 0. So this 0 crossing point can serve as the well, as basically the best value for the mass measurement. So there are some technical details that one has to take into account, and this is, for instance, the statistical uncertainty, of course, and the problem is that at each probe mass, the amplitude of this harmonic is, of course, correlated because they are based on the same sample of events. So we have to deal with the correlations, but this can be treated with the bootstrapping technique. And of course, this technique depends a lot on the vertex resolution we can achieve in the experiment, because at some point, well, for the bad vertex resolution, at some point you will have the decoherence at higher decay times. So this is a very important quantity. And well, of course, the flavor tagging also affects this this technique, but the flavor tagging is very easy to take into account, and by just using this tagging power, which basically scales your effective sample size. So at LHCb, the tagging power is of the order of 5–6% for hadronic final states. Right. So here I'm showing the effect of this final finite vertex resolution. So this somehow deteriorates the structures we see in the flavor asymmetry. So this is for ideal vertex resolution. This is more realistic vertex resolution of 20 micrometers at LHCb, so the transverse one. And this is 40 micrometers, and this is the same thing for the so to say realistic number of events in run 1 and run 2, for instance, for B sub S to D sub S proton antineutron. So this is the kind of pattern you would probably see in the real analysis. So we have measured we have investigated the mass resolution for this technique, and using again the Monte Carlo for the realistic scenario at LHCb with the 40 micrometers transverse, 300 micrometers longitudinal, and the realistic number of events, we get the following numbers here. So you can see that the resolution is actually getting better for higher mass particles. And there is also some bias towards larger masses due to not exactly sinusoidal failure symmetry, but this can be corrected with the Monte Carlo. And this shows you this dependence of the mass resolution on the sample size. And we have also developed the chi-squared like test statistic to measure the signal significance, that there is at least some bis-a-bes signal in the data, taking into account the correlations between the different probe masses. And already with this realistic data sample, we can see that we can achieve rather good signal to background separation. Okay, so I'm concluding here. So we present here the technique that could hopefully help with the partially reconstructed decays at the hadronic machines, that provides us a missing constraints compared to the B factories, and also removes any non-bis-a-bes backgrounds, so it effectively cancels because of those specific pattern of fast bis-a-bes oscillations. So the feasibility depends on the flavor tagging performance and vertex resolution, and we have shown that with the current data set, we can probably hope to see some open charm decays with this technique, but the performance later in run 3 will of course depend on the flavor tagging performance with high multiplicity events. So we have studied this technique using the simple case with two-body decay, where one particle is massive and not reconstructed, and we can see that with this technique we can obtain the spectrum of the masses of these unreconstructed particles, which would be impossible with the other techniques using just topological reconstruction. And the possible applications could be, for instance, searches for new physics with heavy dark matter candidates, or neutrons, K-longs, and so on. But similar techniques can be probably used for semileptonic decays. So instead of probe masses, we will have to use like probe Q-squared or probe angular parameters and so on. And that is me.
Okay, thank you very much, Anton, for this interesting new method. Are there any questions from people connected? We have time for a quick question. Okay, I might have just a generic one. You mentioned at the beginning that, of course, BS is suitable for this because of the fast oscillation, but is there any chance that with slower oscillation of BD, where one can gain much larger statistics, that one can also do such
analysis? Yes, so this question arose during the review of this paper, and it's possible that this could also help with the B0, for instance, and maybe even with the charged, or I mean with the particles that are not oscillating, right? So instead of oscillations, you can just look at the decay pattern, but you will of course lose this advantage of removing the non bis-a-bes backgrounds, because with bis-a-bes, what is unique is that you're basically canceling any non-bis-a-bes stuff.
Yeah, okay, I see. Thank you. Okay, any other questions? Okay, it doesn't seem so. So thank you, Anton, again, and let's move to the next talk by Michal. Thank you. So it will be a talk from Michal Siraski about the flavor physics and discrete symmetries at Cloud 2.
Can you see my screen?
Yes, I can see it very well.
Nice. So I will talk about Cloud and Cloud 2 and how we can use kaons to perform
some nice tests of discrete symmetries and studies of the flavor physics. Let me first introduce you a bit the Chloe and the Daphne. Daphne is a Phi factory on which Chloe was operating for a long time. First as Chloe in early 2000, and then recently from 2013 to 18 as Chloe 2. So as in the first phase, we collected 2.5 inverse femtobarn at the Phi mass peak, because Daphne works at Phi, producing those mesons with very low momentum. At Chloe, it was 15 to 18 MeV. At Chloe 2, with a bit bigger crossing angle, it was 20, 26 MeV. At Chloe 2, we collected, as you can see here on the plot, with the timeline of the measurements, we acquired 5.5 inverse femtobarn, which in total gives the biggest E plus E minus sample collected at the Phi meson mass energy. Now, Phi decays mainly to kaons, as you can see here, and those are charged kaons or neutral kaons, and then also to rho pi and other mesons like eta, eta prime. I will be focused on k short, k long decays. Now, Chloe was operating at one of the crossing points at Daphne. It consists mainly of two parts. One is the big electromagnetic calorimeter, which was modular. We had 24 modules with synthetic fibers and lead. And this gave quite nice performance in terms of time and energy resolutions, and still probably the biggest drift chamber built long time ago, also providing very nice particle identification and resolutions. All those detectors were immersed in the magnetic field of 0.5 Tesla. Now, in the second phase of the experiment with Chloe 2, we inserted other, let's say, supplementary detectors. One was Kukalti for the gamma quanta, which are going towards the quadruples. Here you cannot see them, but they are inside this detector, which is in a tracker. But there was also a Kukalti, which was intending to increase a bit the acceptance with very low angle gamma quanta photons from the pi zero decay, in fact. And we had also first cylindrical gem detector, which was inner tracker, again increasing the acceptance for very low PT tracks. For interested people, there are references which you can where you can find other details. For gamma physics, we had two other detector cells. One was high energy tagger, which was placed 11 meters from the interaction point, just to catch the outgoing electrons and positrons from the process of creation new particles in the E plus E minus collisions and few 12 photons collisions. And then low energy tagger, which was inside the detector, again supplementing this measurement. Those two are used to measure now with Chloe 2 data the gamma, the E plus E minus to E plus E minus pi zero process. Now, the Chloe 2 physics is kind of a broad as for such small experiment, but I will be focusing on kaon physics, in principle the tests of discrete symmetries, but we also can measure many interesting parameters for the hadron physics, for example, or as I mentioned, the pi zero with produced in gamma decays, also some dark force searches. And some of those topics will be presented by my colleague tomorrow. Mostly about the hadron physics. Now, I will present some examples of analysis which are ongoing or were finished not so long ago. One is the K-short to 3 pion decays. There are two. One is K-short to pi plus pi minus pi zero, the other K-short to pi plus to 3 pi zeros. I'm sure everybody here is familiar with this very old story of CP violation in Kaon decays. All those measurements in the past were done for K long. Now, the same amplitudes or the same exercise can be done for K short decays. One can compare the amplitudes of K short going to 3 pions and K long going to 3 pions. Again, we have a kind of parameter which is describing the CP violation. We have the epsilon as in case of K long decays, and additional parameter which is expressing the direct CP violation. And those parameters for K short decays are not very well measured still. For K short to T pi zero, we don't even have the real branching ratio measured. The best upper limit was set by Chloe in 2013, and still is about 1 or more, a bit more, orders of magnitude higher than the standard model prediction, because the standard model prediction is about 2.2 times 10 to the minus 9. Now, for the analogous decay of K short to charged pions and pi zero, there are measurements done indirectly by CP NA48 and other experiments using the K constellations, but directly still nobody saw this decay, and we are going to measure it soon, I hope, with at least 30% precision. Now, the K short to 3 pi zero analysis is also performed now with the new data of Chloe 2 statistics. And let me show you a bit more about this analysis, because I'm involved in this also. So we are looking for 6 photons from pi zero decays. The main background is K short to 2 pi zero process, which is enormous with respect to what we see. And at the end, with the analysis which is ongoing, here you can see the exemplar distribution of the chi-square of the kinematic fit which we performed. We might be able to decrease or the upper limit or reach the sensitivity at about 10 to minus 8, maybe a bit lower, but that's what we can do. Now, we recently measured the asymmetry of the semileptonic decays of K short and K long, which can be expressed as here you see on this slide. This is sensitive to the CP violation, the CPT, possible CPT, and also other, like for example, the delta S delta Q rule amplitudes. This was done by with the first Chloe statistics, and at the end, what we look for are 2 charge tracks and K long in the colorimeter. This is a kind of a nice thing of the factor that you can tag one K on with, for example, interaction or decay of the other. So in this case, we tag with K long interacting in the colorimeter, as also in the case of K short decays to 3 pions. And then we look for 2 tracks which are going out from the interaction point. Again, again we tag, and then we use a control sample of k-long close to IP, tagged by k-short decay to check the analysis and also to estimate better the efficiencies for the decay which we look for. And these are the final plots of the mass defined here as the k-short mass minus energy of the pion and neutrino, which we don't see but we can reconstruct, minus the momenta squared. So here you can see the data and the fit, which at the end give the asymmetry, which is this one. So this is up to now the best results for the k-short. For the k-long, we have much better measurement done by KTEF. But at the end, if those numbers are not consistent, we have proof of CPT violation. Here you can see the KTEF measurement, and then the two measurements of Chloe, one done in 2006, the other new one, which I'm talking about now. And then we also they did a kind of a combination, statistical combination of those two. And between the two sigmas, even less, those are consistent. So we don't see CPT violation yet. Hopefully we don't see it even with better statistics. But at the end, we can reach with the Chloe 2 data a bit better accuracy. Now, the other test which one can do with kaons, and is also very interesting because it's independent on the CPT assumption, is the T and also CPT test in transitions of kaons. So we compare the two states of kaons, either anti-K0, so the one which has very well defined strangeness, with K minus, which is again at the end the state of the CP of the kaon, so with well-defined CP quantum number. Such transitions, K0 to this K minus or K0 K minus to anti-K0 are CPT connected. So at the end, if we compare those two for CPT and also anti-K0 to K minus and K minus to K0, we can test the symmetries. At the end, this is done as a function of the difference in the time of decays of those two kaons or states. And you can define such ratios. We have here at least 4 of them. We can define even more. And those ratios are sensitive to different symmetries. The ratio of R2 and R4, or even single ratios, are sensitive to T, and CPT can be tested with those two on the right. So at the end, for example, if you take the asymptotic shapes of even the ratio of the ratios, this should be 1 and might be lower if we, for example, see some CPT violation expressed by this delta K, or this X minus, which is then corresponding to the delta S delta Q. Now, we basically test all of them. So here you can see the preliminary result of the R2T over R4T, and the fit to the data is consistent with 1, so we don't see yet the T violation. Now that for the CPT, again, we do the ratios of the ratios and to the fit. And here you can see kind of benchmark. This is R4, which is sensitive to CP violation. And we know that in chaos CP is violated. So at the end, the predicted value is written here. It's 1.0064, while this is what we measure in our experiment. So this is still to be finalized, but we have now a preliminary results. And the last which I wanted to talk about is the lepton universality test with the K short to semileptonic decay with muon. This is the first measurement ever done. I mean the branching ratio, and also this corresponds also not only to the lepton universality test, but also the GOS measurement, which is done with several other processes. But again, this is something which contributes. Again, we tag with K-long in the colorimeter. Again, we preselect two tracks from the interaction point. Now the main background, and at the end also the normalization sample which we use to compute the branching ratio is the K short to pi plus pi minus. And there is also a non-negligible background from the phi to K plus K minus, which is then kind of faking the K-long interaction, the colorimeter. We use the BDT algorithm, which is trained with several variables. I don't want to talk about them. I don't have time so much. And then we also perform the time of flight test. Here you can see the data and Monte Carlo description for the BDT. And here we have the one of the variables we used for the test of the time of flight of the particles. At the end, we end up with such kind of distribution where you can clearly see the peak of a signal and the background. The fit to this distribution gives the following branching ratio, which is, I repeat again, the first measurement. And I forgot to say that the efficiencies of this signal selection was estimated by Monte Carlo, and then also by the control sample. And you can see that the comparison between the K short semileptonic decay and K long, because we used again K long as a benchmark for this efficiency. So we have a very nice description of the efficiency. And this brings me to the end. So we have Chloe and Chloe 2 collected the biggest data sample on the phi meson mass energy, which is used to study many processes. In particular, we study K-short decays and transitions to test several discrete symmetries, and those measurements which I showed will be done even better or with better statistics with the Chloe 2 experiment. So thank you very much for your attention.
Give me help for the interesting results from Chloe 2. We are a bit over time, but maybe just a quick question from people connected. Oh. Okay, if not, and then I would like to encourage people to put questions to the MetaMost chat, and we will continue in the program. So thank you, Mikhail, again.
I'm sorry for being so late.
Yeah, that's okay. So thanks, and Giulia, please start with your presentation about the CP evaluation and mixing in charm hadrons and LHCb.
Okay. So let's check. Are you seeing my screen?
Yes. Yeah.
Okay, so hello everyone. Today I will talk about CP violation and mixing in charm hadrons at LHCb. So as you know, charm transition are a unique portal for obtaining a novel access to flavor dynamics. In principle, there might exist some new physics that is coupling only to the uptake quarks, and this is why the study of CP violation in charm is very interesting. However, CP violation in charm is expected to be very small, less than 10 to the minus 3, so it is difficult to observe it experimentally. But finally, last year, LHCb collaboration has observed CP violation also in the charm sector. So now is the time to start a systematic exploration of all the charm hadron decay channel to do a quantitative study of CP violation. And to do this, we need a large sample of charm hadrons, and the LHCb is the perfect experiment to collect them, because the production cross-section for CC bar is about 3 millibar in the LHCb acceptance, and LHCb has collected about 1 billion of these zero decays. Okay, when we talk about CP violation in charm, we need to distinguish between three types of CP violation. CP violation in the decay, CP violation in mixing, and CP violation in the interference between decay and mixing. So in the first case, we have CP violation because the probability of the D0 to decay in a final state is different from the probability of the anti-D0 to decay in the CP conjugate final state. And this is the kind of CP violation that has been observed last year by LHCb. However, we can have CP violation also in the mixing, when the probability of a D0 to oscillate in an anti-D0 is different from the probability of the D0 of the anti-D0 to oscillate in the D0. And we can have also CP violation in the interference between the decay with mixing and the decay without mixing. And there is still no evidence of this mixing-induced CP violation. Okay, let's first go quickly through the first observation of CP violation in charm. To do this measurement, we have used D0 to kk and D0 to pi decays collected during run 2. And to measure the CP violation, we need to tag the D0. To do so, we have used the start to D0 pi decay, where the charge of the pion tagged the flavor of the D0, and also semileptonic decays. So in this case, the flavor of the D0 comes from the charge of the muon. And here you can see the D0 mass and the D star mass distribution for D0 to kk and D0 to pi decays. And in total, we have about 70 million of decays. So the quantity that we want to measure is the CP asymmetry. However, the quantity that we really measure in LHCb is this row asymmetry. So we count the number of D0, we count the number of anti-D0, and then we compute this charge asymmetry. And this row asymmetry is related to the CP asymmetry, but has also contribution from production and detection asymmetry. The production asymmetry is due to the fact that the initial state proton-proton is not CP symmetric, while the detection asymmetry is due, for example, to the fact that the detector is asymmetric. And for the D star plus tag, the production asymmetry is due to the D star production asymmetry, while the detection asymmetry is due to the pion detection asymmetry. In the case of the semileptonic tag, instead, the production asymmetry is the b-hadron production asymmetry, while the detection asymmetry is the muon detection asymmetry. Okay, so these two terms, production and detection, cancel out if we take the difference between the row asymmetry in the two decay channel. So the difference of the row asymmetry is equal to the difference of the CP asymmetry, but the kinematic of the two decay channel needs to be equal. Therefore, to do this, reweighting has been applied to the D0 to kk channel. Okay, so here the results are summarized. So for the run 2, the delta CP has been measured on the prompt sample with a statistical uncertainty of 3.2 times 10 to the minus 4, and on the semileptonic sample with a statistical uncertainty of 8 times 10 to the minus 4. And as you can see, the statistical uncertainty is dominant to the systematic one. So combining these two samples with the run 1 measurement, we can derive the final measurement of delta ICP, which is the first observation of CP violation in charm at 5.3 sigma. Okay, so now let's move to a more recent result on the search of CP violation in the KC plus to PK pi decays, using, in this case, run 1 data. So this is a 3-body decays, so we can make use of the Dalitz plot to look for localized asymmetry. And we can use the lambda C plus to PK pi Cabibbo favored decay as a control channel, because here we expect no CP violation. And here you can see the pk-pi mass distribution for the control channel and for the signal channel. For the control channel, we have about 2 million of total hills, while for the signal, we have about 190,000 hills. Okay, the search has been performed using a binned and an unbinned technique independent from the amplitude modeling of the Dulles plot. For the binned technique, we search for localized asymmetry, comparing the number of baryons and antibaryons bin by bin. So this quantity SCP is calculated, and the presence of global asymmetry, like the detection and production asymmetry, is taken into account using this parameter alpha. Then chi-square is calculated, and the p-value for the null hypothesis is obtained. To be reminded that in the case of no CP violation, the SCP distribution should be a Gaussian distribution with mean 0 and sigma 1. For the unbinned method, a test statistics have been defined, looking at the nearest neighbor in a sample with combined baryons and antibaryons decaying. So this quantity T is calculated, and if no CP violation is present, this quantity is distributed as a Gaussian with the well-known mean and variance. Both methods are sensitive to CP violation greater than 5%, but if there is no CP violation, if the null hypothesis is confirmed, we cannot put an upper limit on CP violation. And here there are the results. So you can see the SCP values on the Dulles plot. And you can see that the distribution is compatible with a Gaussian with mean 0 and sigma 1. And here you have the result for the unbinned method. And the T value has been calculated also in various regions of the Dulles plot. And also in this case, you can see that the null hypothesis is confirmed. Okay, so now let's move to the mixing and the mixing-induced CP violation. So as you know, the mixing arises because the mass eigenstate are a linear combination of flavor eigenstate. And in case of no CP violation, the mixing is described by these X and Y parameters. This is the current experimental status. So as you can see, the mixing now is well established and the no mixing hypothesis stays in 0, 0, while there is still no evidence for CP violation in mixing or interference. In this case, the no CP violation hypothesis stays around 0, 0. So the mixing parameter can be measured using the D0 to K-short pi decays. And here you can see the list of the parameters that can be measured using this channel. So this has been done using round 1 data. And in particular, both the star to D0 pi tagging and semileptonic tagging have been used. And here you can see the mass distribution for the star and semileptonic tag. Okay, so to measure the parameter, the beam flip method has been used. The beam flip method is a model-independent approach which avoids the need for a fit of the decay amplitude. And here you can see on the left the Dulles plot. And the data is binned in the Dulles coordinates, and the binning scheme that you can see on the right plot is chosen to have approximately a constant Strog phase differences. So at the end, a simultaneous fit of the ratio between the plus bin and minus b in bins of the decay time give access to the CP parameters. And here you can see the measured values, so the X and Y CP values and the delta X and delta Y. And all the values are measured with the statistical uncertainties of the order of 10 to the minus 3. And you can see that in all 4 cases, the statistical uncertainty is dominant. Then from the measured values, we can derive the mixing parameter. And in particular, remember that the X parameter is proportional to the difference between the mass of the 2 eigenstates. So the X parameter from this measurement is compatible with 0, but combining with the world average value, we obtain evidence of a positive mass difference between the 2 mass eigenstates. And the run-2 analysis is ongoing. So now I come to my conclusion. So the LHCb experiment has observed direct CP violation for the first time last year. So now we are exploring different decay channels to better clarify the physics picture. New results on round 2 data are coming, so stay tuned. And you don't have to forget that new data will arrive in 2021-2022 with an almost completely new detector and trigger system. The hardware trigger will be removed, and so there will be a bigger trigger efficiency for some channels. and the instantaneous luminosity will increase by a factor of 5. The current results are limited by statistics, so we expect a significant gain in precision with the LHCb Ren 3. So stay tuned, and thanks for the attention.
Thank you very much, Giulia. So are there any questions from people connected? Okay, I would have maybe a naive one for the very last slide. When you talk about this improved trigger efficiency, do you have an idea what is the factor that the efficiency will increase? Is it factor of 2 or?
I mean, it depends on also on the decay channel, but it can also, for some channels, I think that from simulation can be expected also a factor of 5 of increase of the efficiency. But of course, I mean, these things has to be measured on data at the end. So we will see, because at hardware level, there are some cuts, for example, on the transfer momentum that are killing part of the signal. So without the hardware trigger, we will be able to soften some of these cuts. But of course, we have to see during data taking what will happen.
Okay, thank you very much.
Thank you.
So any other questions? Doesn't seem so. So thank you, Giulia, again. Again, people, please use MetaMouse for further questions, and we can continue with the presentation from Kazutaka about the study of time-dependent and direct CP evaluation and Belle.
Hello?
Yes, hello, I can hear you.
Can you see the slide?
Yes, they are not full screen, but if you can try to go full screen, maybe first. Yes, it is very well visible now. Please
okay,
go.
Thank you. I'm talking about the study of a time-dependent and direct CP evaluation at Belle. Fix is 2. Time-dependent CP evaluation in B0 goes to K-shot, 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 and direct CP evaluation in B goes to D0 bar pi. Both results are preliminary result. Then for the CP evaluation, we can measure CP evaluation as the difference of the partial decay width between B and B, something like this. Then interference between two amplitudes with different complex phase make CP evaluation. These two amplitudes make a CP evaluation. This CP evaluation. Then definition of CP evaluation is like this. So in the b-meson system, we mainly use these two types of CP evaluation. One is a direct CP evaluation. We use 2 decay diagrams. For example, K plus pi0 case, one is a tree diagram and one is a penguin diagram. This interference make a CP evaluation. Second method is mixing against the CP evaluation. This is used B0 mixing. One pass B0 decay into a CP eigenstate directly. The other path is through a B0 mixing. Then this interference makes CP evaluation. In that case, since we use a B0 mixing, this CP evaluation as a function of this proper time difference, then it's a time-dependent CP evaluation. This is the equation of this mixing against CP evaluation. Then this term called mixing against CP evaluation in this talk. Then A is the direct CP violation. Then, and CP violation measurement is a good probe of a new physics such, for example, V goes to SQQ but time-dependent CP violation. B0 goes to K-shot is included this category, and it's also one example, delta AK5 hadrons. And KKB accelerator and well detector and like this asymmetric electron-positron rider, something like this. Then this is a well detector, general detector for now E plus E minus colliders. Then we accumulate 772 million BB per data by June 2010, something like this. It's a plot of accumulated record. And we use the parameter, 3 parameter for the signal extraction for both analysis. MVC is a beam constraint mass of a beam meson, and the delta E in the relative difference of a beam meson, and this modified and this variables for to suppress this background. This E plus E minus goes to light QQ bar process is a dominant background for both cases. So we use this event topology to suppress the signal and this background. Then we use some parameter to form using this event topology. Then we combined with variables in artificial neural networks. Then names something like name. Then this is a plot of typical plot of MVC and delta E and this parameter. And the introduction of and the motivation for B0 goes to K-shot. As I say in introduction, this mode is a pure B sub S penguin transition, B to SQQ transition by loop diagram, something like this. Then CP even eigenstate, this final state. Then, and the time-dependent CP variation measurement in the standard model, we have no direct CP violation. And Yixiong induced CP violation parameter is a -9251. Then the deviation from the standard model equation for S and A may indicate a new physics. And then this plot shows the average of a bubble and the Bell and the average. So 1.55 sigma difference between two methods. Then, and this is the final result using full data sample at the Bell. Signal extraction, we use the ambient maximum likelihood fit with a 3-dimensional PDF, delta E and MVC and parameter for continuum suppression. Then we get the 329 plus minus 20 event, and the purity is 72%. Then we use these samples. We extract CP violation parameter using this probability density function, signal PDF and background PDF and outlier PDF, something like this. So this plot shows the proper time difference for the B. Blue plot is the B and the red plot is the B0 bar. and lower plot is a lower symmetry plot, including background. Then fitting result is S equals minus 0.272 plus minus 0.23 plus minus 0.05. A is consistent with no CP violation. Then we estimate the significance of CP violation using Feldman-Cartoons approach. This is the contour plot of vertical axis is the A, horizontal axis is the S. Then this point is present result, and this point is a no CP violation point. So significance of CP violation, our result is 2.4 sigma away from this point. Then this is a present result of S. This is consistent with standard model expectation and previous the result with 1 sigma. Another topic is B goes to direct CP violation. B goes to d0 bar pi. This decay mode is B goes to C U bar D decays like this. So B factory experiment measures something like this, but ACP for now neutral mode is unmeasured yet. Motivation over B goes to d0 bar pi is both decay uses control mode in other analysis. For example, B0 goes to pi plus pi minus, it used phi 2 measurement, and B goes to k pi 0, it's used delta A k pi parallels. Then we use this mode for calibration of validation checks over techniques. So it's important for now Belle II validation frontier. For now, ACP, CP violation, direct CP violation, they have two diagrams, but secondary diagrams is significantly lower amplitude than this main diagram. So expectation in standard model is no CP violation. And the branching fraction also useful for now to study about factorization, but it's skipped. So this is a fit result for the charged mode with the ambient maximum likelihood fit this three parameter MVC delta E and parameter for continuous suppression. And we use a simultaneous fit over 4 this step to sub-decay mode over d0 bar and discharge. Then we get this branching fraction and this direct CP violation parameters. These result are 1.7 improvement in precision before. These result are from neutral mode. Method is basically same as the charged mode. The MVC delta is parameter for continuous suppression and sub-decay mode. K minus pi plus and K minus pi plus pi zero, something like this. So we get this result. For the branching fraction, most precise measurement in this channel and direct CP violation, this result is the first measurement in this channel. It's a summary. I already talked. So that's all over my talk. Thank you very much.
Thank you very much, Kazutaka. So do people have connected questions? Okay, I might have just a quick one on the slide 8. So basically, when you extract the limits and the significance, I see that that obviously the contours that are there are not accounting for this physical boundary of the sum of the square of the amplitudes. Is it? I'm just wondering if the contours would change if the physical boundary was taken into account or not.
Yeah, so we use the Feldman-Gaussian approach.
Okay, I see. Yeah. Okay, any other questions, comments? If not, then in that case, thank you, Kazutaka again, and let's move to the last talk of the session.
Thank you very much.
Thank you very much. So Niharika will present us the measurement of gamma and CP violation first results at Belle II.
Okay, can you hear me?
Yes, a little bit faint. Can you try to be a bit more loud?
Yeah, sorry.
Okay, I think it's fine.
Okay, so you can see my slides now.
Okay, we see the shared screen. Okay, now we can see it.
Okay, so I should start then.
Yeah, please go ahead.
Yeah, okay. So I'll be presenting the measurement of CKM angle phi 3 and the first results of on CP violation at Belle II. So this is the outline of the talk. First is introduction and then some overview about the super KKB oscillator and the Belle II detector. Then Belle II prospects for phi 3 and phi 1 measurement. Then I'll be talking about the first time dependent CPV measurement in the phi 1 and summary. So we are familiar with the CK matrix elements and how the phase that parameterize the CK matrix elements is solely responsible for the standard model description of the CP violation. So in this talk, I'll be mostly focusing on the angles of the unitary triangle, which is and gamma. So there are new physics prospects for these two angles. For example, for phi 1, we can compare the time-dependent CP asymmetries in tree and loop dominated processes. And the difference between these two can directly lead us to the new physics. And for phi 3, we can test the direct versus indirect disagreement, which requires the improvement on the precision on the direct measurements. And this will lead us to the super KKB is a 4 GB positron and a 7 GB electron asymmetric collider at KK Japan. And the designed luminosity is 6 into 10 to the power 35 per centimeter square second, and which is a 30-fold increase in the instantaneous luminosity of KKB oscillator nano beam scheme, where the beam spot size is 20 times smaller, and the beam current is 1.5 times higher than that of Belle. So using this scheme, we'll be able to velocity at super KKB. And the Belle II detector sits at the interaction point, and there are various sub-detectors for different purpose. And as compared to Belle, we have now improved tracking and vertexing, also better particle identification with the new PID detectors, and also better calorimeter resolution. And the challenge along with this is the 20 times higher beam background and the higher trigger rate to cope with. This is the roadmap of the Super KKB oscillator. So now we are here, and there is a long way ahead of us to reach the target luminosity. So as of now, we have we have accumulated 74 femtobarn inverse of dataset, which includes all the runs. And we hope by 2021 summer we'll be accumulating the equivalent dataset of Belle. So please stay tuned with us for more interesting results from Belle II in the next few years. So moving on to the extraction of phi3. So it is the only CCAM angle that is accessible at tree level decays with a very precise theoretical prediction of the order of 10 to the power minus 7. So the classic decay channel used is B to decay. Here I have two quark flow diagrams. One is for the channel favored channel B to decay, and one is for the suppressed one, B to D0 bar K, and the amplitudes of these two decays can be written in terms of the hadronic parameters. And it is measured by the interference of B to D0 K and B to D0 bar K, where D0 can decay to various channels, which includes the CP eigenstates, also the doubly Cabio suppressed modes, and the self-conjugate multibody final states. So in Belle II, the golden channel for phi3 is B2D KD2K short pi pi. So because it has quite a high branching fraction and also the large variation in the D-Dallas plot, which is mostly sensitive to phi3. So we can use the model independent bin-Dallas plot approach, and the number of events in each bin is a function of x and y, which is further a function of the hadronic parameters of interest. So in this, there are two external parameters from the charm factories, which are CI and precision. We require precise strong phase measurement at the charm factories. So we hope the expected 20 femtobarn dataset of BEST 3 will serve this purpose. So it is probably too soon to give a precise measurement on phi3 with the limited dataset of Belle II. But we can surely do some performance checks. For example, here we have rediscovered the channel B2 D pi D2K short pi pi, which is also a control sample for the channel B2 DK D2K short pi pi, which is a golden mode. And there are total 137 signal candidates were obtained with the 2D unbind maximum likelihood fit of delta E and MBC. So as I mentioned earlier, B2DK is the classic channel used for the phi3 extraction, and it is more sensitive to phi3 rather than B2D pi because of its higher RB value. And we had rediscovered B2DK with more than 5 sigma evidence using the continuum suppression tool and the particle identification technique technique of Belle II. So the left delta E distribution is for B2D pi and the D2 the 3 Cabio favored final state without any particle identification. And the right one is with the particle identification criteria on the front pion. So you can see a very nice decay signal peak with 53 signal candidates. This figure here also demonstrates the particle identification power of Belle II. So in future, we expect Belle II and LHCb upgrade to match each other's performance. And with the 50 etoban inverse of dataset, we can reach a precision less than or equal to 1.6 degree. So which will require to include lots of modes, especially the neutral ones, which Belle II is good at reconstructing. And also LHCb will clearly have more precise results with fully charged final states. Moving on to the time-dependent CP violation at Belle II. So we know various type of CP violation, for example, in mixing, in decay, then in the interference of this mixing and decay. So the decay rate of the neutral B meson to a CP eigenstate can be written in terms of delta T and the CP violating parameter from decay and the interference. So to measure the small delta T, at the B factories, the electron and positron are colliding at the asymmetric energies, and to measure the vertex distance difference between these two decays, you can use this. So the key parameters are for time-dependent CP violation is the one is the vertex position measurement and one is the B meson flavor tagging. So for example, here this is the delta T distribution for the neutral B decay. So you can see more details about this in this talk. As I said, flavor tagger is very essential for the CP asymmetry measurement of for phi1 and required for phi1 and phi2. So this is the normalized flavor tagger output distribution for data and Monte Carlo simulation, and you can see a very nice agreement of these two. And this is the dilution factor in terms of the mean dilution obtained from the flavor tagger, and the linearity here shows the agreement of the dilution obtained from the flavor tagger and the measured one within the statistical uncertainty. And to compare the performance, we can say we have already reached effective tagging efficiency of 33.8%, which is comparable with the best of Belle and Babar. So this is the main highlight of this talk, which is the first sin 251 measurement of the channel B2 Jepsai-Kesher. So the sin 251 is the most precisely measured unitary triangle parameter so far. Because it is tree dominated also, and it is theoretically and experimentally precise. So this is the MBC distribution for B2 Jepsai-Kesher, where Jepsai is reconstructed both from electron and muon. And this is the background subtracted delta T distribution and asymmetry as a function of delta T. The fit is performed assuming there is no direct CP violation, and also the reconstruction and the wrong tag fraction for B0 and B0 bar is the same. So from the fit, the sin 251 measured is 0.55 with statistical uncertainty of 0.2, and it is quite a good agreement with the PDG value. So in future challenges both for experiment and theory, the penguin pollution. So it can be controlled experimentally through the channel B to Jepsai pi0. So with just 5/1 inverse of dataset from Belle II, we can reach a value of 0.4 degree of sin 251. Other modes which can also contribute, specifically new physics sensitive, if any significant deviation from B2 Jepsai K-shot is observed. So we had rediscovered B2 phi K-shot, which is new physics sensitive for the first time at Belle II. So this is the delta E distribution for this channel with 16 signal candidates. And the measured branching fraction is 3 into 10 to the power -6, which is in agreement with the world average. Okay, so summary. So flavor physics at high luminosity B factors offers a good flow for testing standard model and looking for new physics. So Belle II will play a key role in this because we have now experience from Belle and Babar, and also it is a good complementarity with LHCb. And with just 5 to 10/1 inverse of dataset, the CKM angles can be, the CKM angle measurements can be improved. And obviously with the huge data set, several measurements are going to be systematically limited. So we have a lots of work ahead. And we just showed the first sign 251 results at Belle II from the channel B to Jepsai Keshav, and it is in good agreement with the world average. And we are expecting the performance to be better with respect to Belle, despite the 20 times higher beam background and lower boost. And looking forward to the next decades of Belle II results. Okay, thank you.
Okay, thank you, Niharika. So are there questions from people connected? Okay, I see she has some questions, so please go ahead.
Hi, it's wonderful to start to see these results coming in from Belle II. I had a question about your the beta decay plots that you showed early in your talk, and I wondered if you had an idea of the efficiency of these PID cuts that you are placing in order to bring out this beta decay peak.
So you mean,
yeah,
here the PID is applied, what is the efficiency for that? It is, I don't have the exact number, it is more than 85%, I guess.
Okay. Thank you very much.
Yeah.
Okay, any other questions? Okay, it doesn't seem to be the case. So by this talk about the future of B physics, one of the main experiments, we have concluded today's session. Again, as also in the previous days, the Zoom room will actually continue for quite a while. So if people want to discuss further any of the talks or any topics from this track, please go ahead. Otherwise, we will see each other again tomorrow at the same basically time slot. So thank you very much for attending, and see you tomorrow.
The following message is best viewed on an oscilloscope.